Water is no longer just a resource, it is a weapon of the future. Across shrinking rivers, massive dams and diversion systems are rising to decide who gets power, who gets food, and who gets left behind. In this documentary, we follow the world's most ambitious water mega projects and uncover the engineering gamble and political pressure behind humanity's attempt to control liquid gold. Overlooking the Peace River, in northeastern British Columbia, the Site C Dam emerged as the third major hydroelectric development on this river, following the Wack Bennett and Peace Canyon dams. Planning for this project involved decades of studies, regulatory reviews, and public consultation before actual construction began in the mid-2010s. Once approved, the first phase of construction focused on site clearing and access preparation. This entailed removing thousands of hectares of vegetation, felling trees, building new access roads, and reinforcing existing ones to accommodate the massive flow of equipment and personnel. Additionally, geotechnical investigations were carried out early to determine subsurface characteristics, which were critical for designing stable foundations in a valley known for its complex geological conditions. Foundation excavation proceeded next, with crews stripping away overburden to expose competent bedrock. This phase involved the use of heavy earth-moving equipment such as hydraulic excavators, bulldozers, and articulated dump trucks, operating on a meticulously choreographed schedule to avoid bottlenecks. Extensive rock bolting and grouting were performed to stabilize the slopes and ensure that water seepage through the foundation would remain within allowable limits. At the same time, river diversion tunnels were being bored through the north bank. These twin tunnels, each several hundred meters long and several meters in diameter, were lined with reinforced concrete and designed to carry the full volume of the Peace River during the dam's construction phase. Once river diversion was in place, the main earth-filled dam structure began to take form. This embankment-type dam required the placement of millions of cubic meters of material in zoned layers, each serving a specific structural or impermeable function. The dam's core consisted of compacted clay designed to be nearly watertight, while the outer shells were built from gravel and rockfill for strength and stability. These layers had to be placed with extreme precision, both in terms of moisture content and compaction density, using a fleet of high-capacity vibratory rollers and GPS-guided dozers. Simultaneously, the powerhouse and spillway complex were under construction on the left bank. These concrete structures demanded an entirely different set of construction techniques, beginning with the erection of massive cofferdams to dewater the work area. Tremie concrete was often used for underwater placements, while large tower cranes and high-capacity formwork systems enabled continuous vertical construction. The powerhouse was designed to house 6 large Francis-type turbine generator units, each requiring massive steel components that were fabricated off-site and transported in modules. Beyond the physical structures, a network of transmission lines was installed to carry the electricity generated at Site C to the provincial grid. These high-voltage lines required the erection of steel lattice towers across challenging terrain with careful coordination to avoid environmental and cultural sensitivities. Environmental mitigation was a persistent theme across all stages of the project, involving fish habitat reconstruction, wildlife corridor planning, and ongoing monitoring of water quality and sediment levels.
The Yimea Community Dam in New Zealand is a significant project aimed at providing a reliable water supply for the Tasman region. The construction of this earth-filled dam involved complex engineering techniques to address the unique geological and environmental challenges of the site. The dam, standing 174 feet tall and 1,210 feet long, is designed to store approximately 13 billion gallons of water. The construction process began with extensive site preparation, including the excavation of a large foundation trench to ensure a stable base for the dam. This involved removing unsuitable materials and replacing them with engineered fill. The foundation was then treated with a combination of grouting and drainage systems to manage groundwater and prevent seepage. These measures are critical for maintaining the dam's structural integrity and ensuring long-term stability. The dam's core is constructed using impervious clay, which acts as a barrier to prevent water from seeping through the structure. This clay core is flanked by zones of carefully compacted earthfill, providing support and stability. The construction of these zones involved precise layering and compaction techniques to ensure that each layer met the required specifications for density and moisture content. This meticulous process helps to prevent settlements and maintain the dam's structural integrity over time. To enhance the dam's safety, a robust spillway system was designed to handle potential overflow during periods of heavy rainfall. The spillway consists of a concrete chute and energy dissipation structures, which are designed to safely convey excess water downstream without causing erosion or damage to the dam. The design and construction of the spillway required careful planning and execution, taking into account the potential impacts of extreme weather events and climate change. The construction of the Yimea Community Dam also included the developments of extensive monitoring and control systems. These systems involve the installation of piezometers, inclinometers, and other instrumentation to monitor the dam's performance and detect any potential issues early. This real-time data is crucial for the ongoing management and maintenance of the dam, ensuring that it operates safely and effectively. The Orville Dam in California, United States, is the tallest dam in the country at 770 feet, underwent significant reconstruction following the spillway failure in 2017. The reconstruction project, completed in 2019, involved extensive engineering and construction efforts to restore the dam's safety and functionality. The reconstruction focused on the main and emergency spillways, both of which were damaged during the 2017 incident. The project began with the demolition of the damaged sections, followed by the excavation and preparation of the foundation. This involved the removal of unstable materials and the installation of drainage systems to manage groundwater and prevent future erosion. The main spillway was reconstructed using high-strength roller-compacted concrete, a technique that involves placing and compacting layers of concrete using heavy rollers. This method provides a durable and erosion-resistant surface, capable of withstanding high water flows. The RCC was placed in layers, each approximately 12 inches thick, and compacted to achieve the required density and strength. The emergency spillway was reinforced with a new concrete weir and an extensive network of concrete walls and slabs, designed to control water flow and prevent erosion. The construction of these structures required precise formwork and concrete placement techniques, ensuring that the new spillway could handle extreme flood events. One of the significant challenges during the reconstruction was managing the continued operation of the dam and reservoir. This required careful coordination and planning, including the use of temporary spillways and water management systems to ensure the safety of downstream communities. The project also involved extensive monitoring and testing to verify the performance of the new structures and ensure compliance with regulatory standards. The Orville Dam reconstruction project demonstrates the application of advanced engineering and construction techniques to address critical infrastructure needs. The project restores the dam's safety and functionality, ensuring the reliable management of California's water resources. The successful completion of this complex and challenging project showcases the capabilities of modern civil engineering to solve significant infrastructure challenges.
It's time for a much more monumental project, the Grand Inga Dam in the Democratic Republic of Congo. Proposed as the largest hydropower project in the world, the Grand Inga Dam has the potential to generate a staggering 40 to 70 gigawatts. It's more than twice the capacity of the three Gorges Dam. The Inga Falls, situated about 225 kilometers southwest of Kinshasa, the capital of DRC, is already home to the smaller Inga 1 and Inga 2 hydropower stations. The project envisions a series of 7 interconnected dams, with Inga III serving as the starting phase. Initially planned at 4,800 megawatts, the design of Inga III was later expanded to 11,000 megawatts. This has increased the total estimated cost of the project to $18 billion, including $4 billion for transmission lines. The Grand Inga Dam would divert the Congo River through the Bundy Valley, creating a vast reservoir to generate power. The unique combination of high water volume, vertical drop, and velocity in the region makes it ideal for hydropower. Each of the proposed 7 power stations would have independent ownership, enabling phased development. The Inga III phase will provide electricity to major stakeholders: 5,000 megawatts to South Africa, 3,000 megawatts to Nigeria, 1,300 megawatts to DRC mining companies, and the remainder to the national utility. This dam could boost industrialization in Africa by providing affordable energy for manufacturing, mining, and urban centers. It is also expected to create jobs, improve access to electricity in rural areas, and reduce reliance on fossil fuels, contributing to global climate goals. In 2018, the DRC government partnered with Chinese and Spanish firms for technical studies and environmental impact assessments. This phase aims to balance the energy generation with socio-economic and environmental considerations. The project has faced significant delays due to financing hurdles, requiring extensive resource mobilization. Additionally, agreements with nations through which transmission lines pass, such as Nigeria and South Africa, need re-evaluation. Several countries and international organizations, including South Africa and the World Bank, have expressed interest in funding and partnering on the project. However, political instability and logistical challenges have delayed progress. The Grand Inga Dam holds transformative potential for Africa, but must overcome significant obstacles to realize its vision of powering a continent. Once completed, the dam could supply clean, renewable energy across Africa, adding to the economic growth and addressing chronic energy shortages. Restoration efforts on the Colorado Big Thompson project have involved a multi-decade sequence of upgrades, structural reinforcements, and modernization of both above-ground and subterranean components across a vast regional network. Spanning trans-mountain diversion tunnels, hydropower facilities, pumping plants, canals, reservoirs, and dam structures, the complexity of renovating this mid-20th century water infrastructure lies not only in the scale of its components, but in the critical, continuous water delivery it must maintain throughout every construction and retrofit phase. At the core of the project is the Alva B. Adams Tunnel, which transports water beneath the Continental Divide. The original tunnel lining, constructed from cast-in-place concrete following drill and blast excavation, has faced decades of hydrostatic pressure, abrasive sediment flow, and thermal expansion stress. Modern inspection robots, equipped with LiDAR and ultrasonic probes, traverse the interior to map defects. Where cracking, voids, or liner degradation is identified, hydrodemolition methods strip the compromised material. Layers of fiber-reinforced shotcrete are then applied, sometimes with embedded stainless mesh or steel lattice reinforcement, to restore structural strength and flow profile. Major valve chambers and penstocks connecting to the hydropower stations have also seen extensive retrofitting. Aging butterfly and cone valves, once manually operated and fabricated from cast iron, are being replaced with stainless steel equivalents that feature automated controls integrated into SCADA systems. Valve replacement requires dewatering and confined space access, necessitating bypass piping and upstream cofferdam installation. In some sites, penstock joints are strengthened with carbon fiber wraps and anchored against slope instability through the use of ground anchors drilled into bedrock. Reservoir and dam structures have undergone re-evaluation to comply with contemporary safety standards, especially in the context of seismic vulnerability and climate-induced hydrological extremes. Earth-filled dams, such as those at Carter Lake and Horsetooth Reservoir, have been subject to slope stability assessments, using modern finite element analysis. Remediation includes flattening embankment slopes, adding chimney drains constructed with well-graded filter sands, and recompacting fill zones to increase seismic resilience. Some dam crests have been raised by several feet to increase freeboard, while auxiliary spillways are being constructed with concrete chute structures lined with energy-dissipating blocks to handle probable maximum flood events. Instrumentation throughout the system has transitioned from analog to digital. Remote monitoring nodes, including piezometers, extensometers, and pressure transducers, feed real-time data into a centralized operations center. This allows for predictive maintenance, dynamic reservoir management, and early warning during extreme weather events. Redundant telemetry paths ensure system integrity even during partial outages. The canal network and siphons responsible for water delivery to Eastern Plains users also required attention. Siphons built from riveted steel pipe were either relined with cured-in-place polymer systems or entirely replaced using slip lining techniques. Open canals were reshaped with laser grading and then lined with concrete or synthetic geomembrane to reduce infiltration losses and improve flow velocity. Turnouts and flow control gates were fitted with actuators and sensors, reducing labor demands and improving response time during flow adjustments. Throughout the renovation, work was heavily constrained by seasonal water demand and the operational requirement to maintain delivery. Construction windows were short, often confined to late fall and winter when irrigation demand was lowest. Shutdowns were planned months in advance and executed with minute-by-minute coordination between contractors and operations personnel. In many cases, redundant systems or emergency bypasses were fabricated in advance to allow full system function while isolated sections were taken offline. Set in the rolling terrain of Fannin County, Texas, the Leonhurst Dam is a key feature in the development of Lake Ralph Hall, a major water supply reservoir under construction to meet the growing demands of the North Texas region. This dam is a crucial component of a broader infrastructure program designed to provide long-term water reliability while incorporating environmental and recreational benefits. The project includes an earthen embankment dam, intake and outlet structures, spillways, and various support facilities. By 2026, the dam embankment, outlet works, and much of the lake basin clearing and impoundment control systems are scheduled for completion, representing the functional establishment of the reservoir. The dam itself is a zoned earthfill embankment, meaning it is constructed using distinct layers of different soil materials, each selected for specific geotechnical properties. The central core is composed of low permeability clay, forming an impermeable barrier to prevent seepage. This core is flanked by progressively more permeable materials, sand, gravel, and rock, that provide both structural support and controlled drainage. These zones are compacted in thin lifts using heavy compaction equipment to achieve the necessary density and bonding between layers. Foundation preparation was one of the earliest and most critical steps in the construction process. It began with stripping of topsoil and removal of organic materials, followed by proof rolling and excavation down to suitable bearing strata. A cut-off trench was excavated beneath the core zone and keyed into bedrock or highly consolidated clay, effectively reducing the risk of underseepage. As an added precaution, grout curtains were drilled along the alignment to seal fractures and enhance subsurface impermeability. As the embankment rose, real-time monitoring was implemented using inclinometers, piezometers, and settlement gauges. These instruments provided engineers with continuous data on pore water pressures, lateral movement, and vertical deformation, allowing timely adjustments to fill placement and moisture conditioning. The upstream slope of the dam was armored with riprap to guard against wave action and erosion once the reservoir reaches operational levels, while the downstream slope was protected with turf reinforcement and slope drains. The outlet work structure, also on track for completion by 2026, consists of a reinforced concrete intake tower, gated conduit, and stilling basin. The intake tower includes multiple inlets at different elevations, allowing selective withdrawal for optimal water quality. Flow from the intake travels through a concrete-lined tunnel beneath the dam, controlled by a series of hydraulically operated gates and valves. At the toe of the dam, flow is discharged into a stilling basin lined with energy dissipation blocks and reinforced slabs to prevent scour and erosion. Spillway construction includes a broad-crested weir and a concrete chute extending down the abutment. The spillway is designed to safely pass the probable maximum flood without overtopping the embankment. It incorporates erosion-resistant lining and aerators to minimize cavitation effects during high-velocity flow events. By 2026, the dam embankment and hydraulic structures will be fully constructed, enabling the initial stages of reservoir impoundment and system commissioning. This milestone signifies the transformation of the site from an active construction zone into a functioning regional water resource, marking a major advancement in North Texas water infrastructure. But what about the Atlantropa, one of the most ambitious and controversial engineering concepts ever imagined in the Strait of Gibraltar? Proposed by German architect Hermann Sergel in the 1920s, the project aimed to drain large parts of the Mediterranean Sea by constructing massive dams at strategic points. The idea was to reclaim vast amounts of land for European settlement, generate immense hydroelectric power, and create a peaceful solution to overpopulation in Europe. During the 1920s and 1930s, Europe faced soaring population growth, rising energy demands, and several geopolitical tensions over land and resources. Sergel's concept, named Atlantropa, proposed to address these challenges by merging Europe and Africa into a single economic and cultural bloc called Eurafrica. He wanted to transform the Mediterranean basin into fertile land, connecting the continents with railways and canals, while using dams to generate hydroelectric power. The project revolved around three massive dams. Strait of Gibraltar, a colossal dam spanning 13 kilometers with a height of 300 to 900 meters, is designed to separate the Mediterranean from the Atlantic Ocean. Dardanelles Strait, another dam to block the connection of the Mediterranean to the Black Sea. Then Sicily, Tunisia, a 150-kilometer dam to split the Mediterranean into western and eastern basins, allowing different water levels for optimal land reclamation. The drained areas would reveal 700,000 square kilometers of land, doubling the size of Germany. The dams would also act as hydroelectric power stations, providing renewable energy for the region. The reclaimed land was envisioned as fertile plains for agriculture and urban development, easing the strain of overpopulation in Europe. The scale of the Atlantropa project was unprecedented. The Strait of Gibraltar Dam alone would have required engineering feats still unachieved today. The construction would involve multiple smaller dams, acting as steps to manage water pressure, inspired by projects like the Zuiderzee works in the Netherlands. The plan also included building canals to maintain trade routes for cities like Venice and Cairo, which would have been stranded inland by the lowered sea levels. The estimated cost of this project was astronomical, over $1 trillion in today's currency. The technology, resources, and international cooperation needed were far beyond what was available. Critics highlighted safety concerns, such as the catastrophic consequences of dam failure and the environmental impact of altering an entire ecosystem. The colonialist undertones of the project also sparked opposition, particularly from African nations wary of European dominance. Despite its grand vision, Atlantropa never materialized. Sergel spent his life advocating for the project, but skepticism and World War II sidelined his dream. After his death in 1952, the idea faded into obscurity. Today, Atlantropa stands as a symbol of human ambition and the complex balance between innovation, environmental stewardship, and social responsibility.
Next up, let's discuss the Glen Canyon Dam that's located on the Colorado River in Arizona. Constructed between 1956 and 1966, the dam was designed to provide water storage, flood control, and hydroelectric power generation for the southwestern United States. The dam created Lake Powell, one of the largest man-made reservoirs in the country, which extends into southern Utah. The construction of the Glen Canyon Dam was a massive undertaking that required extensive planning, innovation, and the overcoming of significant engineering challenges. The dam is a concrete arch-gravity structure standing 710 feet high and 1,560 feet long. It was designed to harness the power of the Colorado River while also providing a stable water supply for agricultural, industrial, and urban use in the region. One of the critical challenges during the construction of the Glen Canyon Dam was the remote location. The site, located in a remote area of the Colorado Plateau, was difficult to access, requiring the construction of roads, bridges, and other infrastructure to support the transport of materials and workers. The dam's construction also involved building the Glen Canyon Bridge, a steel arch bridge that spans 1,271 feet across the canyon, providing essential access to both sides of the construction site. To manage the Colorado River's flow during construction, engineers had to divert the river through tunnels carved into the canyon walls. 2 diversion tunnels, each with a diameter of 41 feet, were excavated through the sandstone bedrock on either side of the river. These tunnels, lined with concrete, allowed the river to bypass the construction site, ensuring that the dam could be built in a dry environment. The foundation of the dam required extensive preparation. Workers excavated the riverbeds down to solid bedrock and ensured a stable foundation for the massive concrete structure. The dam's foundation is key to its stability, allowing it to bear the immense pressure exerted by the reservoir. The concrete used in the dam was placed in blocks, each measuring about 50 feet square and 7.5 feet high. The dam was constructed in a series of these blocks, which were keyed and grounded together to form a solid monolithic structure. The dam's power plant, located at the base of the structure, houses 8 hydroelectric turbines that generate up to 1,320 megawatts of electricity. This power generation capacity has been vital in supporting the electric grid of the southwestern United States. The power plant is also equipped with a series of penstocks, large pipes that carry water from the reservoir to the turbines, allowing for the controlled water release and energy production. It's time to travel over to Turkey next for a record-breaking dam mega project. The Yusufelli Dam stands at 275 meters tall, making it the highest dam located in Turkey and the 5th highest of its kind worldwide. Construction on the Yusufelli Dam began in 2013 and culminated in 2022, transforming the landscape and significantly boosting Turkey's energy capacity. The dam is designed as a double-curvature concrete arch structure. Its crest length extends 490 meters, and the maximum crest elevation reaches 715 meters. This immense structure created a reservoir covering 33.63 square kilometers with a total storage capacity of around 2.2 billion cubic meters. Such a massive reservoir required the precise engineering and use of approximately 220 tons of steel for the gates and 3,800 tons of steel for the penstocks. One of the critical components of the Yusufelli Dam is its power generation capability. The dam houses a 558 megawatt hydroelectric power plant, equipped with 3 vertical axis Francis turbine units, each rated at 186 megawatts. These turbines are designed to operate with a head of 191 meters and discharge of 107 cubic meters per second. The power plant's annual electricity production capacity is approximately 1.9 billion kilowatt hours. The electricity generated is evacuated through a 380 kilovolt switchyard and transmission line integrating it into Turkey's national grid. The construction of the Yusufelli Dam faced numerous geological challenges due to the complex and fractured formations of the Çorum Valley. Extensive geotechnical studies were conducted to understand the site conditions and plan the construction accordingly. Digital 3D geotechnical models were employed to manage the design and construction phases. providing a real-time data and enabling adjustments as excavation progressed. This innovative approach ensured the stability and safety of the dam structure. In addition to the dam and power plant, the project included the construction of significant ancillary infrastructure. 4 balanced cantilever viaducts were built, including the 644-meter-long Pacheco Viaduct and the 695-meter-long Yusufelli Viaduct. Moreover, the project involved constructing 110 kilometers of new roads, 45 tunnels, 22 bridges, and 92 culverts, all designed to support the dam's operation and enhance regional connectivity. The construction process required sophisticated equipment and techniques. The dam's height and curvature demanded precise engineering and the use of advanced construction machinery. Tower cranes with varying capacities, including one 12-ton 280 ECH tower crane, 2 10-ton 200 ECH tower cranes, and 4 6-ton 154 ECH tower cranes were utilized to handle the heavy lifting and placement of materials.
Let's travel over to the Himalayan Mega Dam in China, a colossal structure nestled in the towering peaks of Tibet. Built on the Yarlung Changpo River and often called the Everest of Rivers, this $100 billion project is set to redefine hydropower in the region. Its location in one of the most rugged and remote regions in the world adds to its engineering complexity and significance. The dam is part of China's efforts to achieve carbon neutrality by 2060. It's expected to generate enough clean electricity to power the UK for a year. The Yarlung Changpo features the steepest descent, with its waters plunging over 2,000 meters within a 100-kilometer stretch. This geological phenomenon creates a unique opportunity for hydroelectric generation, but it also presents formidable engineering challenges. The gorge of the river, carved into ancient granite bedrock, is 3 times deeper than the Grand Canyon. This makes it a natural wonder and a high-risk construction zone. The Himalayan region is no stranger to catastrophic flooding. Historical evidence shows that glacially dammed lakes have failed in the past, unleashing devastating outburst floods. Such events have dramatically reshaped the landscape and affected human settlements. These risks loom large over the dam project, as landslides or earthquakes could compromise the structural integrity of the dam. This is indeed a serious threat to downstream communities in India and Bangladesh. Construction on this colossal project began in 2015, and the completion date has not been announced yet. The dam employs state-of-the-art run-of-river hydroelectric systems, reducing the environmental impact by avoiding large reservoirs. Advanced geospatial mapping was used to identify stable construction zones, and cutting-edge tunnel boring machines carved pathways through the rugged terrain. The dam stands at an impressive 315 meters, capable of generating 43.8 million kilowatts of electricity annually. Its power output eclipses that of the Three Gorges Dam, making it the largest hydropower station in the world. Beyond its technical achievements, the Himalayan Mega Dam has far-reaching geopolitical implications. As the Yarlung Changpo flows into India and then into Bangladesh, the dam gives China significant control over water resources critical to millions. This has heightened tensions, with fears that reduced river flow could increase water scarcity in downstream nations. Some experts warn of a potential water war in a region already filled with geopolitical complexities. While the dam promises clean energy, it threatens to disrupt delicate ecosystems and the biodiversity of the river. Downstream communities risk losing vital aquatic resources, similar to the environmental toll seen on the Mekong River from previous Chinese dam projects. Moreover, the river holds profound spiritual significance for Tibetans, symbolizing a sacred goddess. Altering its flow has led to resistance from local communities, who view the project as a violation of their cultural heritage. Despite its challenges, the Himalayan Mega Dam highlights the potential for innovative engineering solutions. By adopting sustainable practices and engaging in international cooperation, there is hope for mitigating environmental and geopolitical risks. But just wait until you hear about one of China's most expensive projects, the South-North Water Transfer Project, with $79 billion already spent. This Chinese mega-project addresses the critical water scarcity issues in the country by transferring water from the resource-rich south to the drought-prone north. The project includes three main routes: the eastern, central, and western lines. The eastern and central routes are operational, supplying water to cities like Beijing, Tianjin, and Shandong province. The western route, still in planning, aims to divert water from the upper reaches of the Yangtze River through the Tibetan Plateau to northern provinces. Spanning over 2,000 kilometers, the project required constructing massive canals, tunnels, pumping stations, and reservoirs. The central route alone diverts 9.5 billion cubic meters of water annually and passes through engineering feats like the Danjiangkou Reservoir. The project is complex and uses TBMs for tunneling, hydraulic drilling machines for dam construction, and high-capacity pumps for testing canal systems. Precision-guided excavators handle massive earth-moving tasks, while automated concrete pouring systems ensure uniformity in canal linings. Advanced monitoring devices are employed to maintain water flow integrity. Due to the topography of the Yangtze Plain and the North China Plain, pumping stations will be employed. They'll raise water from the Yangtze to the Yellow River crossing. Farther north, the water will flow downhill in an aqueduct. The project has brought much-needed water to arid regions, supporting agriculture, industry, and urban growth. By securing water resources for northern economic hubs in China, the project sustains industrial output, urbanization, and population growth. It also reduces reliance on overexploited groundwater, preventing further environmental degradation. Despite its successes, the project has faced significant challenges. Relocation of over 330,000 people to create reservoirs sparked social concerns. Additionally, managing pollution along the routes remains a priority, as water quality directly impacts urban and agricultural usage. Scientists have expressed concerns that the project could increase water evaporation loss. The exact amount of evaporation loss is not known, but it may improve in the future as more water is transferred and the flow rate increases. With more than 40 billion cubic meters of water transferred annually, the project is a lifeline for many regions. Its completion in 2050 will mark a significant milestone in global water management, demonstrating how large-scale infrastructure can address critical resource challenges.
But what about a massive dam megaproject? For that, we have to travel to the Ohio River, where the Olmstead Locks and Dam project is located. This monumental undertaking, designed to replace aging infrastructure and modernize the waterway system, is crucial for the transportation of billions of dollars worth of goods annually across Central States. This project, which officially completed in 2018 after over 30 years of planning and construction, spans across the river and involved an extraordinary financial investment of approximately $3 billion. The construction required the sustained effort of hundreds of engineers, technicians, and laborers over several decades, underscoring the project's scale and complexity. The Olmstead project replaced two older and less efficient facilities, Locks and Dams 52 and 53, which had become increasingly unreliable, causing significant delays in river traffic and logistical inefficiencies. The new structure consists of a navigational pass and two parallel 110-foot by 200-foot locks. This setup significantly eases the river traffic, allowing for the smooth passage of approximately 90 million tons of cargo yearly. One of the notable challenges of the Olmstead Locks and Dam was its innovative construction method, specifically the use of in-the-wet technology. Unlike traditional dry dock methods, this technique involves assembling large modular sections of the dam on land, then floating them to their installation site on the river. The total amount of concrete used in the dam's construction would be enough to pave a sidewalk stretching from New York to San Francisco. A special feature of the Olmstead Locks and Dam is its resilience to seismic activity. The region is near the New Madrid fault line, and as such, the structure was designed to withstand significant earthquakes, ensuring the long-term stability and safety of this critical infrastructure. The project's importance extends beyond just its immediate functionality. By improving the reliability and efficiency of the Ohio River as a navigational channel, the Olmstead Locks and Dam also bolsters the economic viability of river transportation, which is significantly more fuel efficient and environmentally friendly compared to road and rail transport.
Next, it's time to talk about the Itaipu Dam project, located on the borders between Brazil and Paraguay. This colossal structure harnesses the power of the Parana River, generating a staggering 14,000 megawatts of electricity. The dam plays a vital role in the energy supply of both countries, providing approximately 15% of Brazil's electricity needs and 75% of Paraguay's. Construction of the Itaipu Dam began in 1975 and was completed in 1984, involving a massive workforce and significant engineering challenges. The dam itself is about 4.8 miles long and 643 feet high, creating a reservoir that covers an area of 521 square miles. The reservoir, known as the Itaipu Reservoir, has a total storage capacity of 29 billion cubic meters of water. One of the most impressive aspects of the Itaipu Dam is its power generation capability. The dam houses 20 generating units, each with a generating capacity of 700 megawatts. These units utilize Kaplan turbines, which are highly efficient for the varying water flow rates of the Parana River. The power generated is transmitted through high-voltage lines to both Brazil and Paraguay, playing a crucial role in the economic and industrial development of the region. Environmental and social considerations were critical and integral to the project. The construction of the dam necessitated the relocation of around 40,000 people and significant ecological changes, including the creation of the Itaipu Biological Reserve to protect wildlife. The project also involved extensive reforestation efforts and the establishment of fish hatcheries to mitigate the environmental impact. Managed jointly by Brazil and Paraguay through the Itaipu binational entity, it stands as a testament of what can be achieved through collaboration.
But how about a barrier megaproject that will protect an entire city? Venice, a city renowned for its unique architecture and intricate waterways, has been facing an existential threat from flooding due to rising sea levels and sinking foundations. In response, Italy embarked on one of the most ambitious and technically complex engineering projects in Europe, the Venice Flood Barrier, officially known as the MOSE project. Initiated in 2003, the project comprises a series of 78 mobile underwater gates designed to temporarily isolate the Venetian lagoon from the Adriatic Sea during high tides. Spanning 3 inlets that connect the lagoon to the sea, each gate measures 20 meters wide and weighs up to 300 tons. When not in use, these gates rest in caissons on the seafloor filled with water. During high tides, air is pumped into these caissons, causing the gates to rise and block the incoming water. The technical challenges of constructing such a system were immense. Engineers had to develop new materials and methods to ensure the gates could withstand the harsh marine environment, including building special corrosion-resistant barriers that could endure for decades. The project also involved massive dredging operations to lay the foundations of the gates, moving millions of cubic meters of seabed. But besides those challenges, delays and cost overruns were frequent as well, pushing the project's completion date several times. The initial budget ballooned from an estimated $1.6 billion to an eventual total of $5.7 billion, making it one of the most expensive megaprojects in Europe. Unlike conventional dams or levees, the Venice Flood Barrier is designed to be both invisible and temporary, appearing only when needed to protect the historic city.
But next up, we have to talk about the Site C Dam in Canada, a critical project located on the Peace River in northeastern British Columbia. Located just 14 kilometers southwest of Fort St. John, this project is the latest addition to the network of dams in British Columbia. Soon, it will become the 4th largest hydroelectric producer in the province. When operational in 2025, Site C will generate 1,100 megawatts of electricity, supplying enough clean energy to power approximately 45,000 homes annually. The project is intended to provide a reliable and affordable source of clean electricity for more than 100 years. It will also stabilize energy costs and support industries like mining and forestry. The idea for Site C emerged in the 1970s, following the successful completion of the WAC Bennett Dam and Peace Canyon Dam, also on the Peace River. Initially delayed due to environmental concerns and fluctuating energy demands, the project was revived in the early 2000s. Construction finally began in 2015, after contentious debates over its necessity and impact on the local ecosystem and communities. Site C is a $16 billion initiative employing cutting-edge engineering and construction techniques. The dam features an earthfill structure standing 60 meters tall and spanning over 1,050 meters across the river. The construction involves extensive diversion tunnels to redirect the river during the building process. Colossal machinery is employed for the installation of large-scale turbines capable of generating 4,600 GWh of electricity annually. The project also includes a spillway and powerhouse, where water flow is converted into clean energy. Advanced geotechnical stabilization methods ensure the resilience of the structure, even in challenging seismic conditions. While Site C promises sustainable energy, it has faced significant opposition. The dam's reservoir will flood 5,500 hectares of agricultural land, destroying fertile soil and impacting wildlife habitats. It is responsible for putting indigenous burial grounds, traditional hunting and fishing areas, and habitats for more than 100 species vulnerable to extinction. This has drawn criticism from environmentalists and Treaty 8 First Nations, who argue that the project violates their rights and disrupts traditional practices. Site C has further been affected by delays, budget increases, and legal challenges from opponents. The pandemic further disrupted construction schedules, adding to the complexities of the project. Despite these setbacks, the government remains committed to completing the dam, with an operational target of 2025. The Site C Dam is the most expensive public infrastructure project in the history of British Columbia. However, it has a much lower capacity than the Robert Bourassa, the largest dam and hydro project in northern Quebec. Next, we have to talk about one of the biggest dams constructed in China, the Longtan Dam. Located on the Hongshui River in Guangxi Province, this $4.2 billion project is one of the tallest roller-compacted concrete dams in the world, standing at 216.5 meters. The Longtan Dam was built to generate hydroelectric power, improve flood control, and enhance navigation along the river. Completed in 2009, the dam stands 216.5 meters tall and stretches 849 meters in length. Its 6,426 MW of capacity makes it one of the largest hydropower stations in China, supplying clean energy to millions of households and industries. Constructed using roller-compacted concrete, the Longtan Dam features a unique design that enhances its strength and efficiency. The reservoir capacity is a staggering 27.3 billion cubic meters, with an active capacity of 16.2 billion cubic meters. The gross head of the dam measures 179 meters, enabling its power station to achieve a colossal installed capacity of 6,426 MW. This includes 7 turbines, each with a capacity of 700 MW, along with 2 additional turbines added in a later phase. The electricity generated by Longtan is sold to China's Southern Power Grid, meeting the power demands of millions while reducing reliance on fossil fuels. The dam also plays a critical role in flood control, irrigation, and water supply management, contributing to regional stability and development. Furthermore, its presence aligns with the commitment of China to renewable energy, significantly reducing carbon emissions. While the dam provides significant benefits, it also comes with environmental costs. Its construction displaced over 8,000 people and submerged 300 square kilometers of land, including forests and farmland. Efforts have been made to relocate affected communities and mitigate ecological damage. One of the notable features of the dam is its ship lift, which allows vessels to bypass the dam and continue along the river. This has improved trade and transportation in the region, boosting local economies. The Longtan Dam faced challenges during its construction, including geological issues and public opposition. However, its successful completion has cemented its role as a vital component of the energy and water management strategy implemented by China. Today, the Longtan Dam has become a popular tourist destination, drawing visitors to marvel at its sheer scale and engineering brilliance. The Syano-Shushenskaya Dam in Russia is one of the most iconic hydropower stations in the world. Located on the Yenisei River in Siberia, this $1.2 billion project stands at an impressive 242 meters, making it one of the tallest dams ever. Stretching across a length of 1066 meters, this arch-gravity dam is a critical component of hydropower infrastructure in Russia. The dam was built to utilize the immense flow of the Yenisei River for power generation and flood control. The reservoir, with a storage capacity of 31.3 cubic kilometers, provides consistent water flow for year-round electricity production. Designed to withstand earthquakes up to 8 on the Richter scale, the dam showcases exceptional structural resilience, even earning a place in the Guinness Book of World Records for its unique construction. The Syano-Shushenskaya power station has an installed capacity of 6,400 megawatts and generates approximately 23,500 GWh of electricity annually. The 10 turbines in the dam, each rated at 640 megawatts, operate with incredible efficiency. The reservoir also ensures steady water flow during peak energy demand, adding to the energy security of Russia. In 2009, the dam faced one of its greatest challenges. A catastrophic turbine malfunction caused a massive flood in the turbine hall, resulting in 75 fatalities and extensive structural damage. Power generation was severely reduced, and the accident raised concerns about operational safety. Following the tragedy, an intensive $1 billion rehabilitation and modernization program was undertaken between 2010 and 2014. This effort restored the full capacity of the dam and incorporated advanced monitoring and safety systems to prevent future incidents. The dam plays a pivotal role in reducing the reliance of Russia on fossil fuels, contributing significantly to its renewable energy output. It also supports regional agriculture and industry by providing reliable water management. Despite its immense scale, the dam's integration into the Syano-Shushenskaya Nature Reserve reflects a balance between energy production and environmental preservation.
Gorges Dam in the United States is being expanded to nearly double its current capacity, making it one of the largest dam expansion projects in the country. The project involves raising the dam height by 131 feet, which will increase the reservoir's capacity from 42,000 acre-feet to 119 acre-feet. This expansion requires significant engineering and construction efforts, including the use of roller-compacted concrete to construct the new dam structure. The construction process begins with extensive site preparation, including the excavation of the existing dam and the construction of temporary diversion tunnels to redirect water flow. The diversion tunnels are critical to maintaining river flow and minimizing the impact on downstream ecosystems during construction. Once the site is prepared, the foundation is laid using high-strength concrete to ensure stability and durability. RCC is a type of concrete that is placed and compacted using earth-moving equipment, allowing for the rapid construction of large-scale concrete structures. The RCC is placed in layers, which are then compacted using vibratory rollers to ensure maximum density and strength. This method is highly efficient and allows for faster construction times compared to traditional concrete pouring methods. The use of RCC also reduces the amount of formwork required, as the concrete is placed in large quantities and compacted in place. This reduces the need for extensive scaffolding and supports, further speeding up the construction process. The construction of the new spillways and outlet works is also a critical component of the project, ensuring the safety and stability of the dam. The spillways are designed to handle extreme flood events, while the outlet works control the release of water for downstream use. The project also includes the installation of advanced monitoring systems to ensure the dam's safety and performance. These systems include sensors and instruments that monitor the dam's structural integrity, water levels, and environmental conditions in real time. The data collected is used to make informed decisions about dam operations and maintenance. Tehri Dam in India is one of the largest and most complex dam projects in the country. Located on the Bhagirathi River in Uttarakhand, the dam stands at a height of 853 feet and creates a reservoir with a capacity of 2.6 million acre-feet. The construction of Tehri Dam involves several significant engineering challenges, including the dam's foundation in a seismically active region and the need to manage a large volume of water. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tehri Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,000 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines.
Let's move over to the Three Gorges Dam in China, towering over the Yangtze River in Hubei province. Completed in 2006, after 17 years of construction, it is the largest hydropower project in the world. Built at a cost of approximately $28 billion, it serves multiple purposes, including flood control, hydroelectric power generation, and improving river navigation. First proposed in the early 20th century, the dam was envisioned as a solution to the Yangtze River's devastating floods. The river, spanning thousands of kilometers, is prone to flooding that has historically claimed thousands of lives and caused immense economic damage. Construction began in 1994 with the primary goal of reducing flood risks and generating clean energy. This dam symbolizes modernity and progress preferred by China. Stretching 2,335 meters across and standing 181 meters tall, the dam's scale is monumental. Its reservoir extends 660 kilometers upstream, creating a water storage capacity of 22 billion cubic meters. The dam operates 34 massive turbines, producing a combined output of 22.5 gigawatts, enough to power millions of homes annually. This energy production reduces reliance on coal, significantly cutting greenhouse gas emissions. The construction involved massive earth-moving operations and precise placement of reinforced concrete. Workers used diversion canals to redirect the Yangtze's flow, enabling the dam's foundation to be laid. The dam has 5-tier ship locks at each end that allow vessels up to 1,000 tons to pass. It also has a ship lift that can raise cargo ships up to 1,800 tons. While the dam provides immense benefits, it has come with steep costs. Over 1.2 million residents were displaced to make way for the reservoir, impacting local communities. Environmental concerns include disrupted sediment flow, which affects aquatic ecosystems and downstream biodiversity. The altered river flow has also led to increased landslides and erosion along the edges of the reservoir. Designed to mitigate flooding, the dam regulates water flow by holding rainwater in its reservoir during the rainy season. However, critics argue that its storage capacity, while vast, can only manage 9% of extreme floodwaters. In severe conditions, the limits of the dam are exposed, leading to debates about its long-term effectiveness. Despite its success, the dam has been criticized for increasing seismic activity and causing landslides due to the immense weight of the reservoir. concerns about water quality and sedimentation have also emerged, highlighting the need for ongoing management and research.
Tarbella Dam in Pakistan is one of the largest earth-filled dams in the world, located on the Indus River. The dam stands at a height of 485 feet and creates a reservoir with a capacity of 11.62 million acre-feet. The construction of Tarbella Dam involved several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tarbella Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 3,478 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines. Sardar Sarovar Dam in India is one of the largest and most complex dam projects in the country. Located on the Narmada River in Gujarat, the dam stands at a height of 535 feet and creates a reservoir with a capacity of 7.7 million acre-feet. The construction of Sardar Sarovar Dam involves several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Sardar Sarovar Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,450 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines.
Next up, we have to talk about the Grand Coulee Dam, an engineering masterpiece and one of the largest infrastructure projects in United States history. Built during the Great Depression, its construction spanned from 1933 to 1942, offering much-needed employment and economic stimulus to the region. Located on the Columbia River in Washington state, the dam is a cornerstone of American hydropower, irrigation, and water management. The dam was conceived as part of President Franklin D. Roosevelt's New Deal, aimed at boosting economic recovery through large infrastructure projects. Its dual purpose was to generate hydroelectric power and irrigate vast tracts of arid land. This was all about transforming the Columbia River Basin into a fertile agricultural region. With a length of 1.6 kilometers and a height of 168 meters, it is one of the largest concrete structures in the world. Today, it produces 6,800 megawatts of electricity, supplying power to 2 million homes annually. The reservoir of the dam, Franklin D. Roosevelt Lake, irrigates over 600,000 acres of farmland, driving agricultural productivity. Additionally, the power plants in the dam supply electricity to millions, facilitating industrial growth and regional development. The Grand Coulee Dam stretches 1,592 meters across the Columbia River and rises 168 meters from its granite foundation. It required a staggering 11.9 million cubic yards of concrete, 3 times that used in the Hoover Dam. Its thickness ranges from 30 feet at the top to 500 feet at the base. The dam houses 4 power plants, including the left and right power plants, each equipped with 9 generators, rated at 125 megawatts each. A later addition, the third power plant, features 6 generators, 3 of which boast a capacity of 805 megawatts each, making it a powerhouse of energy production. The total generating capacity of the dam is 6,809 megawatts, sufficient to power millions of homes and industries. Building the Grand Coulee Dam required innovative techniques, including individual penstocks, giant pipes up to 40 feet in diameter, to carry water to the generators. A labor force of over 8,000 workers at its peak tackled harsh weather conditions and complex engineering challenges. The spillway, spanning 1,300 feet, was designed to handle massive water flows, protecting the structure from flooding. The Grand Coulee Dam has not only transformed the Columbia River Basin into an agricultural haven, but also ensured energy security for the Pacific Northwest. Its contribution to irrigation, flood control, and recreation has solidified its status as an engineering marvel. Today, the dam attracts tourists worldwide and offers educational tours. There's an annual laser light show that celebrates its monumental history and technological significance.
We can't overlook the massive Clamath River project. With a price tag of $450 million, this project involves removing 4 hydroelectric dams to restore natural fish migration patterns and improve water quality. For over a century, these dams have blocked vital fish habitats, and the removal is set to be completed by the end of 2024. This will open up 400 miles of river for species like Chinook salmon and steelhead trout. Let's dive into the engineering behind this transformative project. The 4 dams planned for removal are known as the Lower Klamath Project. They include the J.C. Boyle, Copco No. 1, Copco No. 2, and Iron Gate dams. These dams were originally built for hydroelectric power generation, but they've also severely disrupted natural water flow and fish migration for decades. So how do you remove dams that stood for a century? At J.C. Boyle Dam, an existing drain that was originally built to divert water during the construction of the dam will be used to drain the reservoir. Concrete step logs currently blocking this drain will be blasted open to allow the water to flow through. Once the reservoir is drained, workers will begin demolishing the dam structure itself. Meanwhile, at Copco No. 1, engineers will drill a new tunnel through the base of the dam. This tunnel will act as a controlled release point for water. The demolition crews will use drilling and blasting techniques to dismantle Copco No. 2 and Iron Gate Dam. The goal of this project isn't just about removing dams, it's about restoring an entire ecosystem. The Clamath River project is the largest dam removal project in U.S. history. It's part of a growing movement to rethink how we manage natural resources, prioritizing ecosystem health and sustainability over industrial infrastructure. Projects like this set a powerful example for future ecological restoration efforts. Over 76,000 cubic meters of concrete and 2,000 tons of steel will be removed. Nearly 1 million cubic meters of material will be excavated to return the river to its natural state.
Welcome to the Muskrat Falls project, a colossal hydroelectric power station on the lower Churchill River in Labrador. Did you know that the Muskrat Falls project spans over 100 square kilometers? The project harnesses the power of water, generating up to 824 megawatts of electricity, enough to light up over 500,000 homes. Construction kicked off in 2013 and, amidst various challenges, wrapped up in late 2020. The scale of this endeavor is staggering, with a final cost soaring to approximately 12.7 billion Canadian dollars. Originally estimated at 7.4 billion, the financial scope ballooned due to unforeseen geological challenges and logistical complexities. The construction of the dam itself is a feat to behold. The main dam, made from over 2.2 million cubic meters of concrete, stretches across 32 meters in height and an impressive 432 meters in length. The project utilized innovative construction techniques, such as the extensive use of large-scale prefabricated modules to speed up the construction process and reduce the environmental impact. The harsh weather conditions of Labrador, with freezing temperatures and heavy snow, tested the mettle of every worker on site. Muskrat Falls also integrates cutting-edge technology with a series of 204-kilometer transmission lines, known as the Labrador Island Link, which connect the power generated from the falls to the population centers. This technological marvel includes software that allows the power flow to be adjusted in real time, optimizing energy distribution based on current demand and supply conditions. Muskrat Falls is connected to the island of Newfoundland by a subsea cable spanning nearly 30 kilometers across the seabed of the Strait of Belle Isle. This is one of the longest subsea electricity cables in the world, a little shorter than the length of Manhattan.
Let's talk about the Kranoyasque Hydroelectric Project, located on the Nelson River in Canada. This project has a total capacity of 695 megawatts and is designed to harness the power of the Nelson River to generate renewable energy. The primary structure of the Kranoyasque Hydroelectric Project is the generating station, which consists of a concrete powerhouse housing 7 turbine generator units. The Kranoyasque project includes 7 dams with a combined length of nearly 24 kilometers and 2 large dikes designed to control water flow and create the necessary head for power generation. The powerhouse and spillway structure were constructed using large quantities of reinforced concrete, with the total concrete volume used in the project exceeding 700,000 cubic meters. The turbine and generator units at Kranoyasque are Kaplan turbines, chosen for their efficiency in harnessing the variable flow of the Nelson River. The installation process included the careful alignment of the turbine shafts and the precise calibration of the generator units to ensure optimal performance. Let's investigate the next mega project called the Alisud Dam. Located on the Tigris River in southeastern Turkey, the project represents a major engineering and construction feat. This dam is a key component of Turkey's southeastern Anatolia project, which aims to harness the region's water resources for energy production, flood control, and irrigation. Construction of the Alisud Dam began in 2006 and concluded in 2020. Standing 135 meters tall and stretching 1,820 meters across, the dam is a concrete-faced rock-filled structure. It has an embankment volume of 43.8 million cubic meters and creates a reservoir with a capacity of 10.4 billion cubic meters. This reservoir is essential for the dam's primary purpose of hydroelectric power generation, with an installed capacity of 1,200 megawatts from 6 Francis turbines, each producing 204 megawatts, generating about 3,833 gigawatt-hours of electricity annually. The dam's construction involves significant engineering challenges due to the region's complex geological and hydrological conditions. To manage these challenges, the Tigris River was diverted through 3 large circular diversion tunnels, each with a diameter of 12 meters and lengths ranging from 897 to 1,099 meters. This diversion was critical to keep the construction site dry, allowing for the building of the dam's foundation and ensuring a stable working environment. A key structural component of the Alisud Dam is its sophisticated spillway system, designed to manage floodwaters efficiently. This system includes a chute and energy dissipation structures, crucial for controlling the flow of water released from the reservoir and protecting downstream areas from potential flooding. Additionally, the power plant, which houses the turbines, features state-of-the-art digital governors, shutoff valves, and ancillary systems to ensure efficient and reliable operation. Throughout its construction, the project encountered financial and logistical challenges. Initially funded by export credit agencies from Germany, Switzerland, and Austria, these backers withdrew in 2009 due to Turkey's inability to meet over 150 international environmental and social standards. Consequently, Turkey secured alternative funding through public and private bank loans, showcasing the government's commitment to completing the project despite international setbacks. The engineering work also included the construction of substantial infrastructure to support the dam. A 250-meter permanent steel girder bridge was built downstream to facilitate the transport of materials and equipment. Moreover, the project required extensive roadworks, including raising and repairing 52 kilometers of bridge to accommodate the construction needs. The powerhouse of the Alisud Dam is equipped with 6 vertical Francis turbines, each with a capacity of 204 megawatts and 6 generators rated at 223 megavolt amperes. These components are housed in a facility designed to optimize efficiency and safety. The tail race tunnel, approximately 1,100 meters long with a maximum width of 143 meters, directs water safely away from the powerhouse, ensuring smooth operation. One of the significant engineering achievements of the Alisud Dam is its ability to integrate advanced technology with practical construction methods. The dam's design and execution require a collaborative effort from various engineering and construction firms, employing modern techniques to address the region's unique challenges.
But just wait until you hear about one of Russia's most iconic megaprojects, the Kranoyasque Dam. Built on the Yenisei River near Krasnoyarsk in Siberia, this massive hydroelectric dam is a landmark of Soviet-era engineering and a vital part of power grids in Russia. Completed in 1972, the Kranoyasque Dam is a gravity dam that stretches 1065 meters across the Yenisei River and stands 124 meters tall. With an installed capacity of 6,000 megawatts, it generates enough electricity to power industries and homes across the Krasnoyarsk region and beyond. The dam is particularly crucial for supplying energy to the Krasnoyarsk aluminum smelter, one of the largest in the world. The Krasnoyarsk Dam features a 600-meter wide spillway capable of discharging 2,000 cubic meters of water per second. The reservoir of the dam, known as the Krasnoyarsk Reservoir or Krasnoyarsk Sea, stretches over 2,000 kilometers and holds a staggering 73.3 billion cubic meters of water. One of the standout features of the dam is its ship lift, a unique engineering solution that allows vessels to bypass the dam by moving over its massive structure. This lift, one of the largest of its kind, facilitates transportation along the Yenisei River, connecting Siberia to the Arctic Ocean. The creation of the Krasnoyarsk Reservoir flooded vast areas of forest and farmland, displacing thousands of people. It also disrupted local ecosystems and altered the natural flow of the river. However, the dam provides critical flood control, protecting downstream communities from seasonal flooding. The Krasnoyarsk Dam plays a key role in supporting the industrial economy of Russia. Its reliable energy output ensures the smooth operation of heavy industries like aluminium production, which are essential for both domestic use and export. The dam also serves as a significant source of employment and regional development. Despite its benefits, the Krasnoyarsk Dam has faced criticism for its environmental impact and the social costs of its construction. Nevertheless, it remains a symbol of Soviet-era ambition and a testament to the power of hydropower in driving economic growth. Unlike conventional bridge construction that relies on in-place assembly over active roadways, the 2nd Avenue Bridge replacement over I-94 in Detroit took a bold and modern approach, building the entire structure off-site and moving it into position in a single, coordinated operation. This method, known as self-propelled modular transport, allowed engineers to reduce highway closures dramatically while executing a highly complex structural replacement with precision and control. The original 2nd Avenue Bridge was a narrow, outdated crossing that no longer met the safety or capacity standards required for urban connectivity in the Midtown Detroit corridor. With the ongoing modernization of the I-94 freeway, it became essential to not only replace the bridge, but to do so in a way that minimized impacts to one of the busiest traffic arteries in the state. Traditional staged construction would have required extended lane closures, ongoing detours, and multiple phases spread out over months or even years. Instead, the project team designed a new, wider bridge structure that would be constructed entirely adjacent to the interstate in a staging area. This new structure, composed of steel plate girders and a concrete deck, was built on temporary supports known as falsework towers. The substructure, comprising abutments and approach walls, was prepared well in advance at the final bridge site using cast-in-place concrete supported on deep foundations, including driven H-piles embedded into firm strata beneath the interstate. Once the off-site construction was complete and all systems verified, the move operation was scheduled for a carefully planned weekend closure of I-94. The actual bridge move was performed using SPMTs, multi-axle, computer-controlled transport platforms capable of lifting and carrying massive loads with millimeter-level accuracy. The entire superstructure was lifted off its temporary falsework supports using hydraulic jacks integrated into the SPMTs. The system then slowly transported the bridge across the staging area, maneuvering over prepared access paths and aligning itself precisely with the final bridge bearings. During this process, crews on site continuously monitored bearing alignment, elevation, and lateral position, ensuring the bridge matched its abutment seat locations exactly. Once the bridge was in final position, it was slowly lowered onto elastomeric bearings, and mechanical connections were secured to tie the structure into the existing roadway network. The final stages of the operation included backfilling approach zones, paving transitions, and installing barriers and utilities, all tasks that had been prepared in advance to accelerate reopening. One major advantage of this move-in-place approach was that it compressed months of disruptive work into a matter of days. Rather than subjecting the corridor to prolonged construction noise, lane reductions, and detours, the SPMT method enabled a near instantaneous installation with minimal long-term disruption. In central Ohio, the Intel Ohio Semiconductor Campus, Phase 1, is one of the most closely watched industrial megaprojects tied to the United States manufacturing build-out in the second half of the decade. It is designed as the first stage of a large semiconductor production complex near Columbus, with Phase 1 centered on 2 leading-edge chip fabrication plants and the extensive support infrastructure required to operate them. In any 2026 completion discussion, this project has to be described as a major construction and delivery milestone rather than a simple fully finished campus, because semiconductor facilities are completed through overlapping stages of shell construction, utility activation, clean room installation, equipment move-in, and production ramp. Phase 1 is significant because a semiconductor fab is not only a large building, it is a highly controlled, industrial system made up of clean rooms, vibration-managed foundations, chemical delivery networks, water treatment systems, power distribution equipment, air handling systems, process piping, backup systems, and security-controlled production space. The visible structures are only one part of the build. Much of the project's complexity is in the hidden technical infrastructure that allows fabrication tools to operate within extremely strict environmental tolerances. The construction work associated with reaching key 2026 milestones is concentrated on finishing the main fab structures, closing the building envelope, completing mechanical and electrical plant systems, and pushing the site from heavy civil work into interior technical fit-out. By that stage, work includes structural steel and concrete completion, where still ongoing utility corridor development, substation and power infrastructure advancement, installation of water and wastewater systems, process piping, HVAC systems, cleanroom framing, raised floor systems, filtration equipment, and the commissioning of support buildings that serve the fabs. Exterior works also remain important, including internal roads, drainage, logistics areas, and the site-wide infrastructure needed for a campus that is expected to expand in later phases. A critical distinction for semiconductor projects is the difference between construction completion and operational readiness. Even if major building work reaches an advanced state in 2026, that does not automatically mean full chip production begins immediately. After the physical facilities are largely complete, there is usually a long sequence of cleanroom certification, systems balancing, contamination control verification, specialty equipment installation, tool hookup, process testing, and early production qualification. That means 2026 is best understood as a year of major physical completion and systems transition for Phase 1, with final industrial readiness depending on how quickly the project moves through commissioning and tool installation. By 2026, Brickell City Center, Phase 2 is taking shape as a continuation of one of Miami's most influential mixed-use districts, with construction focused on adding new vertical density while expanding the pedestrian and retail ecosystem already established in Phase 1. In a city where projects must be delivered without shutting down surrounding streets, Phase 2 is built as a live integration job, tying new towers and public space upgrades into an operating urban complex. Construction activity in 2026 typically begins with the parts the public barely sees. Crews are deep into foundation and below-grade work, including drilled shafts, matte foundations, and waterproofed basement slabs designed for Miami's high water table. Utility reroutes and new service corridors are being installed early because Phase 2 has to expand electrical capacity, chilled water distribution, and telecom backbones without interrupting Phase 1 operations. Stormwater capture and pumping systems are also being upgraded to handle larger roof areas. New plazas, and intensified runoff in heavy rain events. Vertical construction in 2026 centers on the first major towers and podium structures. Concrete cores rise first to establish elevator shafts, stairwells, and riser pathways, followed by floor plate pours on a repetitive cycle. As soon as lower levels are enclosed, curtain wall installation begins to create weather-tight zones, allowing interior trades to move in while structural work continues above. This year's progress is measured by how quickly the project transitions from raw structure to concurrent fit-out. Because Brickell City Center is known for high-performance public realm features, 2026 work also includes extensive streetscape and circulation construction. Pedestrian bridges, widened sidewalks, and redesigned drop-off zones are built in phases to maintain access to existing retail and transit connections. Traffic control modifications, signal timing upgrades, and loading dock routing are being implemented too. Manage delivery volumes and rideshare demand that increase as new components come online. Inside the new structures, mechanical and electrical installation is a major 2026 driver. Contractors are routing large duct mains, chilled water piping, fire protection systems, and emergency power pathways. Mixed-use buildings add complexity, so hotel, office, and residential zones, if included, require separate vertical risers, access control strategies, and dedicated back-of-house circulation. Data and security systems are embedded early, including fiber distribution, camera infrastructure, and building automation networks that will manage energy use across the expanded footprint. Retail and podium levels, where foot traffic concentrates, receive early attention in 2026. Structural framing and slab work are paired with rough-ins for grease exhaust, kitchen ventilation, and high-capacity electrical feeds that support food and beverage tenants. Public-facing finishes typically lag the structural schedule, but the groundwork for storefront glazing, escalators, and vertical circulation is installed now to avoid rework later. Timeline-wise, large mixed-use expansions like this are generally delivered as phased openings rather than a single completion date. In a 2026 construction context, Phase 2 is usually positioned for major structural milestones in the near term, followed by a multi-year sequence of enclosure, interior completion, tenant build-outs, and commissioning. The practical completion window is commonly late 2020s, with different components opening as they clear inspections and operational readiness. In the Las Vegas Valley, the Intermountain Health Children's Hospital project is one of Nevada's most consequential healthcare builds, still under construction in 2026. The facility is being delivered as a dedicated pediatric hospital designed to expand specialty care capacity, reduce the need for families to travel out of state, and create a modern hub for children's emergency, inpatient, and surgical services. By 2026, the project is in its intensive build-out phase. The structural frame and building enclosure are advancing, and the construction focus has shifted toward the systems that make a hospital function safely. Mechanical, electrical, and plumbing trades are installing the backbone infrastructure floor by floor: large air handling units, medical gas lines, fire protection piping, and redundant electrical distribution. Critical care spaces require strict air pressure relationships and infection control measures, so 2026 work includes commissioning of HVAC zones, sealing of penetrations, and installation of filtration systems sized for operating rooms, isolation rooms, and neonatal care environments. Interior construction in 2026 is also defined by specialized build requirements. Patient rooms are framed and roughed in with head walls that integrate oxygen, vacuum, data, and nurse call systems. Imaging areas require structural support and shielding coordination, so contractors are placing lead-lined assemblies, vibration mitigation, and dedicated power feeds for MRI, CT, and interventional equipment. Surgical suites and procedure rooms move through a tightly sequenced workflow in 2026. Wall framing, above-ceiling service booms, low-voltage integration, and cleanable finish packages designed for infection prevention. Outside the building, site infrastructure remains active in 2026. Work includes final grading, stormwater management, and the construction of ambulance and service access routes that separate emergency circulation from public drop-offs. Utility tie-ins are a major task this year, especially for redundant power and backup generation. Hospitals require continuous operation, so 2026 construction includes generator yard installation, fuel systems, automatic transfer switches, and testing protocols that verify the facility can sustain critical loads during grid outages. Technology integration is another defining 2026 scope item. Data closets, fiber runs, and wireless infrastructure are being installed early because clinical systems depend on reliable connectivity. Security and access control systems are layered in as areas are enclosed, including camera networks, controlled staff entries, and infant security features typical of pediatric facilities. In 2026, one of California's most vital water infrastructure projects is under full-scale construction in the western Sacramento Valley. The site's reservoir project, located northwest of Sacramento near the community of Maxwell in Colusa County, is a planned off-stream reservoir with a total capacity of up to 1.5 million acre-feet. Unlike traditional on-stream reservoirs, sites will store water diverted from the Sacramento River during high-flow periods, reducing flood risk while creating a critical reserve for drought resilience. The project entered its primary construction phase in 2026, following final approvals, funding commitments, and site preparation work completed in preceding years. Grading, excavation, and embankment work are active across multiple fronts, including the main site's dam and Golden Gate Dam, both of which will form the eastern and western boundaries of the reservoir basin. These earthen embankment dams will rise approximately 310 feet above the valley floor and span over 4,000 feet in length, designed to safely contain the seasonal floodwaters diverted via a complex network of conveyance infrastructure. Construction of the associated intake facilities on the Sacramento River near the existing Red Bluff and Colusa Basin regions is also progressing in 2026. These facilities will include fish screens, pumping stations, and underground pipelines designed to divert excess winter and spring flows into the reservoir while maintaining compliance with environmental flow standards. Twin conveyance pipelines, approximately 14 miles long, are being installed to transport the diverted water westward to the reservoir basin. At the same time, work is advancing on the terminal regulating reservoir, located near Dunnigan, which will play a role in distributing stored water to the existing Central Valley Project and State Water Project networks. This integration allows site's reservoir to serve multiple uses: agricultural irrigation, urban supply, wildlife refuges, and ecosystem support, particularly in dry years when water deliveries are traditionally curtailed. The reservoir's location was selected in part due to its off-stream design, which minimizes disruption to fish migration and river ecology while allowing water storage flexibility. In 2026, foundation treatment, compaction, and embankment fill placement are underway, utilizing local materials sourced from adjacent borough sites. The volume of material movement is extensive, with millions of cubic yards being relocated and compacted to form the primary dam structures. Concrete structures, including control towers, outlet works, and spillways, are also in early stages of placement. The site's project authority, which oversees the project, expects major civil works to continue through at least 2029. By then, reservoir impoundment and system testing will begin. Full operational readiness is projected for the early 2030s, although water deliveries could begin earlier depending on hydrological conditions and infrastructure completion rates. The construction effort in 2026 employs hundreds of workers and involves coordination with federal, state, and regional water agencies. At the heart of a massive cross-border logistics corridor between Detroit, Michigan, and Windsor, Ontario, the Gordie Howe International Bridge emerges as one of the most technically ambitious and strategically vital infrastructure projects in North America. Designed as a cable-stayed bridge with an unprecedented main span length for this type of crossing in North America, the structure addresses not only current transportation needs, but also anticipates decades of future commercial and passenger vehicle growth. What sets this project apart is the integration of border processing facilities on both ends, a multi-use path for non-motorized users, and a focus on minimizing environmental impact during construction. Construction of the bridge began with an intensive ground improvement phase. On both the Canadian and American sides, the project required deep foundation stabilization due to soft soils and industrial legacy conditions. Thousands of concrete-filled steel piles were driven deep into the ground, many over 150 feet long, to support the massive load of the main pylons and approach structures. Vibrocompaction and dynamic replacement techniques were also applied in select areas to densify weak soils and ensure long-term settlement control. The signature feature of the bridge is its cable-stayed main span, which stretches more than 2,500 feet across the Detroit River. The two massive towers, each rising nearly 150 meters above the water, were constructed using climbing formwork systems with high-strength reinforced concrete placed in lifts and allowed to cure under strictly controlled environmental conditions. Each lift required careful coordination of embedded rebar cages, conduit for internal inspection systems, and multiple layers of quality control for alignment and geometric accuracy. The stay cables are arranged in a semi-fan pattern and connect to a composite steel concrete deck that is fabricated in modular segments. These segments are lifted into position by strand-jacking gantries placed atop the towers, and then post-tensioned into place as the structure progresses outward from both pylons in a balanced cantilever method. Because of the immense forces involved, cable anchorage zones in the deck were heavily reinforced and constructed using high-performance concrete to prevent cracking and fatigue over the bridge's lifespan. In parallel with the main span construction, the approach structures required extensive use of precast girders and segmental concrete box girders, supported on piers founded on deep drilled shafts and pile caps. Each approach segment had to be aligned precisely with the main span geometry to allow seamless connection once the cantilevers met at mid-span. Expansion joints, seismic isolation bearings, and cable dampers were installed to accommodate temperature changes, traffic vibrations, and potential wind-induced oscillations. Perhaps one of the most unique aspects of the Gordie Howe International Bridge is the inclusion of full customs and inspection plazas on both sides of the river, which had to be constructed concurrently with the bridge. These facilities involve complex building systems, large-scale pavement infrastructure, and real-time data integration with transportation networks. Stormwater management, energy efficiency, and border security technologies were embedded into their design from the outset. Across the Northeast Corridor, the Gateway Program's Hudson River Tunnel component is one of the most consequential transportation megaprojects in the United States. But in a 2026 focused video, it should be framed as a project reaching critical construction acceleration rather than full end-of-project completion. Its purpose is to build new passenger rail tunnels under the Hudson River between New Jersey and Manhattan, and then allow the existing century-old tunnels, which were heavily damaged by saltwater intrusion during Hurricane Sandy, to be rehabilitated without cutting the region's rail capacity in half. That is why the project is treated as a national infrastructure priority rather than a local rail upgrade. The core problem is capacity and reliability. The existing two-track tunnel is a bottleneck for intercity and commuter rail traffic entering Penn Station. It carries Amtrak and NJ Transit trains on the busiest passenger rail segment in the country, yet it lacks redundancy. Any major service disruption affects travel across the Northeast. The new tunnel project is intended to solve that by adding parallel tunnel capacity first, creating the conditions for later rehabilitation of the old tubes while maintaining service. The important point is that 2026 is associated with major active construction and package-level milestones, not with the final opening of the full tunnel system to passengers. In that year, the key work is expected to include continued heavy civil construction on approach structures, tunnel portal, areas, retaining structures, utility relocation, ground improvement, excavation support, concrete works, and early tunnel-related infrastructure on both sides of the river. Where contracts are advanced enough, 2026 activity also includes site preparation for full tunneling operations, staging areas, access shafts, and the supporting infrastructure needed before boring or immersed structural progress can translate into final rail systems installation. The project is unusually complex because it is not only a tunnel beneath a major river. It has to connect into one of the most constrained rail environments in North America. On the Manhattan side, work must interface with Penn Station approaches, densely developed urban blocks, utilities, transportation corridors, and existing rail operations. On the New Jersey side, the alignment must tie into the broader network while managing wetlands, embankments, and active right-of-way conditions. Every phase depends on sequencing, civil, structures, ventilation and safety provisions, drainage, trackbed preparation, and future system spaces all have to be coordinated long before trains can operate. Another major issue for the 2026 timeline is that the Gateway program is not a single construction contract. It is a portfolio of interdependent elements, including tunnels, portal works, bridge-related interfaces, and supporting rail infrastructure. Because of that, completion can mean different things depending on the contract package being discussed. Some enabling components may reach major completion earlier, but the overall Hudson River Tunnel element remains part of a longer delivery schedule extending beyond 2026. North of downtown Miami's traditional core, Miami World Center in 2026 functions as a multi-site construction zone rather than a single project, with separate towers, public streets, and retail blocks being delivered in overlapping packages. In the Miami Megaproject landscape, under construction in 2026, its defining feature is sequencing. Infrastructure and public realm upgrades must be completed while new vertical buildings rise on adjacent parcels, all tied into an active transit district. In 2026, civil and streetscape construction is a major component of the work. Crews are completing permanent roadways through the district, adding new intersections, curb lines, and pedestrian crossings that stitch the development into the existing street grid. Utility expansion is continuous this year, including new water and sewer runs, stormwater piping, and electrical duct banks sized for high-rise loads. Because the site sits in a dense urban area, much of this work is staged block by block, with temporary traffic shifts and night work used to maintain access to existing businesses and transit corridors. Vertical construction continues in 2026 across multiple towers and podium structures. Concrete cores rise first, followed by repetitive floor plate pours and post-tensioning cycles that allow multiple high-rise teams to work in parallel. Curtain wall installation is advancing on lower levels to create weather-tight zones for interior trades, which is essential in Miami's rain-heavy seasons. As soon as floors are enclosed, mechanical, electrical, and plumbing rough-ins accelerate, including fire protection systems, vertical risers, and building automation infrastructure. Retail and entertainment components are being built out in 2026 as a network, not as isolated storefronts. That means interior shells are being delivered with coordinated grease exhaust, kitchen ventilation, and high-capacity electrical service for food, beverage, and nightlife tenants. Loading and waste management routes are being finalized behind the scenes to keep service traffic separated from pedestrian promenades. Public lighting, security cameras, and wayfinding systems are being installed early because the district is expected to operate in phases, with some blocks active while others remain under construction. Parking and mobility integration is another visible 2026 construction task. Garage structures and podium parking levels are being completed alongside pedestrian links that connect to nearby transit, including Metro Rail and Brightline access points, rideshare staging zones, bus interfaces, and protected pedestrian routes are being built to manage event peaks without overwhelming surrounding streets. Because Miami World Center is a long horizon development, its timeline is defined by phased completions rather than a single opening date. By 2026, earlier components are already operating, while new towers, hotel additions, and street-level blocks continue to come online in stages. The late 2000s are generally positioned as a period when multiple remaining parcels reach completion, with full district build-out extending further depending on market absorption and project sequencing. By 2026, the Las Vegas Convention Center Loop is no longer just a single-site people mover. It is a construction program aimed at pushing a tunnel-based circulation system beyond the convention campus and into a broader visitor corridor. The extension's work in Nevada in 2026 is defined by repetitive tunneling cycles, station construction, and the practical challenges of building underground in a city that never really shuts down. Construction in 2026 typically starts with utilities and access. Before a tunnel boring machine can advance, crews relocate water, power, telecom, and storm systems, then build launch pits, reception pits, and temporary shafts that support excavation, muck removal, and segment delivery. These enabling works are visible at street level as fenced compounds, slurry handling areas, and staged concrete pours for shaft walls and base slabs. Once tunneling is active, 2026 work focuses on advancing short to medium tunnel drives between new station locations. Crews manage ground support, lining installation, and continuous surveying to keep the alignment precise, because station interfaces and turnouts rely on tight geometry. Spoil haulage is constant, with trucks cycling in and out, and ventilation systems running to keep underground conditions safe for crews and equipment. Stations are the most time-consuming elements, and in 2026, they are where the project becomes a civil and architectural build rather than a pure tunneling job. Excavation and shoring come first, then cast in place concrete for platforms, ramps, and vertical circulation cores. After the structure is complete, contractors move into waterproofing, drainage, electrical rooms, fire life safety equipment, and finishing work such as lighting, signage, and passenger queuing areas. Because these are vehicle-based stations, 2026 construction also includes roadway tie-ins, curb work, and traffic control redesign at each portal, so vehicles can enter and exit without creating bottlenecks. Systems integration is a major 2026 focus across the extension network. That includes communications backbones, CCTV, access control, emergency lighting, and ventilation monitoring tied into centralized operations. Even though vehicles provide the passenger movement, the tunnel still functions like a transit facility underground, so emergency egress paths, suppression systems, and incident response procedures drive a large share of the installation and testing schedule. A defining feature of 2026 is phased delivery. Extensions are typically opened segment by segment as stations and tunnel links are completed, tested, and permitted, rather than waiting for an entire map to be finished at once. That means 2026 construction often overlaps with commissioning on earlier segments, including test runs, safety drills, staff training, and integration of new stations into the operating headways and dispatch patterns. In 2026, several major extensions of the Bay Area Rapid Transit System are under construction, forming a critical part of Northern California's long-term transit infrastructure strategy. The largest and most technically complex is the Silicon Valley Phase 2 extension, a 6-mile expansion of BART service from Berryessa, North San Jose, to downtown San Jose and Santa Clara. This project is being led by the Santa Clara Valley Transportation Authority in partnership with BART and is a federally funded multi-billion-dollar endeavor. Construction in 2026 is fully active along the entire Phase 2 alignment. The project includes 4 new stations: 28th Street, Little Portugal, downtown San Jose, Diridon, and Santa Clara. Approximately 5 miles of the alignment will be constructed using a single-bore tunnel, 45 feet in diameter, making it one of the largest subway tunnel sections in North America. In 2026, tunneling operations are scheduled to begin following completion of launch shaft excavation and assembly of the tunnel boring machine. Shaft construction and staging zones are already established at multiple sites, including the western portal near Diridon Station. The downtown San Jose station, which will be built underground, presents specific challenges due to its depth and proximity to active utilities, heritage buildings, and seismic zones. In 2026, deep excavation, support of excavation walls, and early concrete pours are underway. Similar substructure work is progressing at 28th Street and Diridon, where retained cut and mined station boxes are being constructed. Cut and cover methods are being used at the Santa Clara station, which will serve as the new western terminus of the extension and will include a surface-level tail track and storage tracks. The entire Phase 2 extension is projected to open for revenue service by 2036, with major civil work and tunneling expected to conclude by the early 2030s. The project's integration with existing transit hubs, including Caltrain, Amtrak, VTA Light Rail, and future California High-Speed Rail at Diridon, is a key element of the design. In 2026, intermodal design coordination is ongoing between BART, VTA, Caltrain, and city agencies to synchronize platforms, vertical circulation, and fare systems. Elsewhere in the Bay Area, BART is continuing with other network improvement projects in 2026. This includes planning and pre-construction for the potential extension to Livermore along the I-580 corridor. Although not yet in full construction, right-of-way acquisition and environmental reviews are active. This corridor is intended to close a critical gap between Dublin, Pleasanton, and the Tri-Valley region. Throughout Central and Southern California in 2026, university campuses are undergoing large-scale construction to accommodate rising enrollment, research expansion, and updated sustainability mandates. These developments span multiple University of California and California State University institutions, with a focus on housing, laboratories, medical infrastructure, and renewable energy integration. At the University of California, Merced, construction continues on multiple academic and housing facilities under the 2020 Project Phase 2, expanding the campus's capacity well beyond its original footprint. In 2026, vertical construction is active on new science and engineering buildings, along with residential halls that will add over 1,000 new beds by 2027. These additions support UC Merced's long-term goal to serve over 15,000 students and enhance its research output in agricultural technology and climate science. Beneath the southern skyline of Portland, Oregon, the Cellwood Bridge replacement project unfolded as a carefully orchestrated effort to modernize a century-old crossing while respecting the constraints of an urban setting and a sensitive river environment. Originally opened in 1925, the existing structure had long been structurally deficient and functionally obsolete. It carried tens of thousands of vehicles per day on a narrow, deteriorating deck with no shoulders and minimal pedestrian accommodations. The new bridge would not only replace the failing structure, but also vastly improve safety, seismic resilience, and multimodal capacity. The design of the replacement bridge called for a deck arch structure, which would span the Willamette River with minimal disruption to the waterway and surrounding neighborhoods. Prior to any new construction, engineers faced the unique challenge of what to do with the existing bridge. Instead of fully demolishing it up front, a temporary solution was implemented. The original steel truss was shifted laterally, intact, onto temporary piers constructed just downstream. This extraordinary lateral slide operation allowed the old bridge to remain in service while the new bridge was built in its original alignment. The lateral move required precise hydraulic jacking systems and heavy-duty rollers. Crews disconnected the truss from its existing piers and then slowly slid the entire structure onto a set of temporary supports built on drilled shafts. This move, executed in just a few hours after weeks of preparation, cleared the path for demolition of the original concrete piers, many of which had suffered extensive corrosion and were no longer structurally viable. With the original alignment clear, construction of the new bridge began with installation of deep foundation elements, including drilled shafts socketed into bedrock beneath the riverbed. These shafts would support the new reinforced concrete piers, which in turn carried the load of the deck arch. The arch segments were constructed using a balanced cantilever method, with concrete segments cast in place and post-tension to maintain structural integrity as they extended symmetrically from each side of the river. The bridge deck itself was cast in segments atop the arch ribs using a system of falsework and custom-formed travelers. The deck accommodated 2 standard travel lanes in each direction, generous bike lanes, and wide sidewalks on both sides, features entirely absent from the original structure. In addition, the deck design included integrated stormwater treatment systems to capture and filter runoff before it entered the Willamette River. As the new bridge took shape, utilities were relocated, traffic patterns shifted, and seismic isolators were installed beneath critical components to provide flexibility in the event of an earthquake. Steel reinforcement was designed with corrosion resistance in mind, and all concrete elements were specified with admixtures tailored to the region's wet climate. Once the new structure was complete and fully operational, the old temporary bridge was dismantled and removed from its temporary supports. Final phases included landscaping, approach road improvements, and installation of aesthetic lighting and railing features to blend the bridge with its urban and natural context. North of Phoenix, the TSMC Arizona Semiconductor Fab project is one of the most important industrial construction programs tied to United States megaproject delivery in 2026. But it has to be described in phases because the site includes multiple fabrication plants and supporting facilities with different completion and production timelines. The Arizona development is designed as a high-end semiconductor manufacturing campus with fabrication buildings, utility plants, clean room space, water systems, power infrastructure, chemical handling systems, administrative areas, and logistics support all built as one integrated production environment rather than as isolated factory shells. Its importance comes from the nature of semiconductor manufacturing. A fab is not complete when the structure is topped out. The visible building is only the outer layer of a much more complex technical system. Below and inside the shell are vibration-sensitive slabs, redundant power feeds, process cooling, ultra-pure water generation, wastewater treatment, specialty gas delivery, chemical distribution, air filtration, and clean room infrastructure that must operate to extremely tight tolerances. That means the final construction stages in 2026 are driven less by general building work and more by technical fit-out, systems integration, and equipment readiness. For a 2026 megaproject completion discussion, the Arizona Fab site is best understood as reaching major completion milestones during that year, rather than finishing every long-term phase of the campus at once. The key construction activities in 2026 are likely centered on interior cleanroom completion, mechanical and electrical plant finalization, process utility installation, hookup of manufacturing support systems, and the transition from base building, construction into tool installation and commissioning. Work at that stage typically includes completion of air handling units, duct systems, chilled water and condenser systems, chemical piping, specialty gas cabinets, exhaust systems, clean room ceilings, raised access floors where required, control systems, fire life safety integration, and final testing of building performance. Another defining issue is the distinction between construction completion and production start. Once the fab building and support systems are finished, the project still has to move through cleanroom certification, contamination control verification, installation of lithography and process tools, utility hookups to each tool, calibration, pilot runs, and yield qualification. Because of that sequence, 2026 should be treated as a year in which construction is completing the conditions for operations, even if the manufacturing ramp continues beyond the point at which the buildings themselves appear finished. Across downtown Miami's development pipeline, Okan Tower is one of the most technically demanding high-rise builds discussed for the 2026 megaproject landscape because it combines a near super tall structure with hotel, residential, and amenity users stacked in a single vertical system. The project's design is defined by a tapered, curving profile that requires non-repeating formwork, tight survey control, and careful coordination between facade geometry and the concrete core. For a tower of this height class, the construction story in 2026 is typically about structure, enclosure, and building systems moving in parallel. Vertical concrete work is the pacing item, with the central core climbing ahead of the floor plates to keep elevators, stairs, and mechanical risers on schedule. High-rise crews cycle through rebar placement, post-tensioning, and slab pours, then immediately follow with perimeter edge forms that lock in the tower's changing shape as it rises. Facade work becomes a second critical path in 2026. Curtain wall panels are installed from the lower levels upward to create weather-tight floors that can transition into interior build-out while structure continues above. Because Miami's climate is humid and storm-prone, 2026 enclosure work includes water management detailing, pressure testing of facade zones, and robust waterproofing around balcony edges, window interfaces, and podium transitions. Mechanical and electrical installation expands rapidly during this phase. In 2026, contractors route chilled water and condenser systems, build out air handling rooms, and install vertical shafts for smoke control and stair pressurization. Electrical distribution grows floor by floor, with switchgear, risers, and backup power pathways installed early to support life safety systems, elevators, and the dense loads that come with hotel operations. Mixed-use towers add complexity because different occupancies have different requirements. In 2026, construction sequencing must separate hotel back-of-house routes from residential circulation while maintaining code-compliant egress and fire separation between zones. That translates into additional rated assemblies, dedicated service elevators, and separate mechanical distribution strategies, all coordinated before finishes can proceed. Amenity and public-facing components also shape 2026 work. Where the tower includes a signature pool deck or rooftop amenity, crews build transfer slabs, waterproofing systems, and structural supports that can carry heavy live loads and mechanical equipment. Street-level podium work, including retail shells and drop-off zones, is usually being fitted out in 2026 as well, with storefront glazing, loading access, and traffic interface improvements installed to support eventual operations. Set just east of downtown Reno, the Grand Sierra Resort expansion is, in 2026, a live construction program aimed at turning an already large casino hotel into a broader, year-round campus for lodging, events, sports, and entertainment. What makes it a Nevada mega project this year is not a single building, but the way multiple upgrades are being sequenced to keep the resort operating while new capacity is added around it. In 2026, the most visible work is vertical and structural. Crews are focused on building out new venue space and additional hotel capacity in phases, which typically means steel erection, concrete deck pours, and enclosure work first, followed by systems installation and interior fit-out. Where the expansion includes a large event or arena-style component, 2026 construction concentrates on long-span framing, rigging points, and the structural bays needed for lighting grids, catwalks, and back-of-house loading. That structural package has to be finished early because everything from scoreboards to stage systems depends on embedded supports. Mechanical and electrical work becomes a major driver in 2026 because Reno's climate demands both heating and cooling, and large assembly spaces require high air change rates and smoke control capability. Contractors are installing air handling units, duct mains, and vertical shafts while routing chilled water, hot water, and fire protection piping through congested ceiling zones. Electrical teams are expanding service capacity with new switchgear, upgraded transformers, and redundant distribution paths to support gaming floors, kitchens, and event production loads simultaneously. Site circulation is also being rebuilt in 2026 to handle higher peak volumes. That includes reworking drop-off zones, rideshare staging, service roads, and pedestrian connections between the resort core and new amenities. Utility trenching is active during this phase because expansions often require new stormwater infrastructure, upgraded sanitary connections, and expanded telecom and fiber capacity for ticketing, security, and broadcast. Parking and wayfinding improvements typically follow close behind, with phased paving, striping, and lighting upgrades scheduled to avoid interrupting major weekend demand. Interior progress in 2026 is less flashy but critical. Where new hotel floors or renovated room blocks are part of the plan, crews are moving through repetitive build cycles: framing, MEP, rough-in, drywall, finishes, and then commissioning. For new food and beverage areas and banquet support, 2026 work includes grease waste systems, ventilation hoods, and high-capacity electrical feeds, all installed early to avoid rework once finishes go in. In 2026, construction begins in earnest on the Los Angeles Metro Southeast Gateway Line, a major light rail expansion aimed at delivering high-capacity transit service to some of the most densely populated and historically underserved communities in southeast Los Angeles County. Previously known as the West Santa Ana Branch Transit Corridor, this project represents one of the largest new rail corridors in the region and forms a critical part of the county's long-term Measure M mobility strategy. The project's first operational phase will span 14.5 miles, linking the existing A-Line station at Slauson in South Los Angeles to a new terminal station at Pioneer Boulevard in Artesia. This segment will include 9 new stations and is designed to serve communities across Huntington Park, Bell, Cudahy, Southgate, Downey, Paramount, Bellflower, and Artesia. As of 2026, the corridor is in the early stages of pre-construction and enabling works, with heavy utility, relocation, environmental mitigation, and corridor preparation now underway. Utility relocation is a primary focus in 2026. In multiple cities along the alignment, electrical, gas, water, and telecommunications lines are being moved to accommodate future construction of the light rail guideway and associated infrastructure. In Artesia, crews are also performing grading work and beginning access improvements in preparation for major station excavation and track installation, which is expected to ramp up in 2027. The project is being delivered under a progressive design-build model. A joint venture of Flatiron, Dragados USA, and Herzog is leading the initial pre-construction phase under a contract valued at over $997 million. This early work includes soil testing, demolition of outdated facilities, geotechnical surveys, and engineering refinements along the right-of-way. These preparatory efforts are critical to mitigating delays once full construction begins. The total cost? For the Southeast Gateway Line, Phase 1 is projected at approximately $8.6 billion. The project is being funded through a combination of local sales tax measures, including Measures R and M, along with state transportation funds and a significant request for federal support through the FTA's New Starts Capital Investment Program. Metro is targeting a full funding grant agreement from the federal government by 2027. The alignment follows a former Pacific Electric Railway corridor with portions of the route adjacent to active freight lines. In 2026, Metro and its construction partners are actively coordinating with freight rail operators to ensure clearances, right-of-way agreements, and safety systems are in place. Quiet zones, grade separation structures, and fencing are being designed, and in some areas, early site work has begun. The line will use low-floor light rail vehicles, similar to those operating on Metro's existing lines, with stations designed for full ADA accessibility. Platforms, traction power substations, and signal control infrastructure are all in the design phase in 2026, with final engineering packages expected to be released for construction bidding in 2027. In an environment where minimizing disruption to major interstate corridors is paramount, the I-95 bridge replacement in Westport, Connecticut, demonstrated the full potential of accelerated bridge construction methods, specifically the lateral slide technique. This project involved replacing a structurally deficient bridge over Saugatuck Avenue, one of the busiest stretches of I-95 in the region, and doing so within a matter of days rather than months. The strategy required meticulous preparation, extensive off-site construction, and flawless execution during a very short highway closure window. The existing structure, carrying both northbound and southbound traffic, had reached the end of its service life. Deterioration in the substructure and deck made full replacement necessary, but the surrounding context, a dense suburban area with no practical detour options, meant that a traditional replacement approach was unfeasible. Engineers turned to a plan that would pre-build the new bridge spans adjacent to the existing alignment, then slide them into position during a single, carefully scheduled weekend closure of I-95. Before anything could be moved, a complex network of temporary supports, approach transitions, and hydraulic jacking systems had to be prepared. Construction crews built the new bridge structures on temporary foundations parallel to the active highway lanes. These new spans consisted of precast concrete deck panels integrated with steel girders, forming a composite superstructure. All connections, reinforcements, drainage components, and lighting conduits were pre-installed to reduce on-site finishing work after the move. While traffic continued to flow on the existing bridge, crews below worked on the new bridge's final foundation and abutment construction. These included concrete abutments supported by deep foundation systems such as driven piles, along with bearing pads designed specifically to accept the sliding load. The horizontal slide surface was engineered using Teflon-coated pads and stainless steel slide tracks designed to minimize friction during the move. When the designated closure window arrived, the entire section of I-95 was shut down, and demolition crews moved quickly to remove the existing bridge. This required heavy excavators, saw-cutting equipment, and debris haulers working in synchronized shifts to clear the area within hours. As soon as the old structure was out of the way, hydraulic jacks were engaged to push the new bridge spans laterally onto the permanent abutments. This slide was conducted at a controlled pace, typically a few feet per hour, with continuous monitoring to ensure alignment, levelness, and bearing engagement. Once the new bridge was in place, the final phase included forming and pouring the deck closure joints, completing the approach slabs, connecting utility runs, applying waterproofing membranes, and finishing the surface paving. Precast parapets and guardrails were already attached to the new deck, eliminating the need for extensive post-move safety installations. Within just a few days, traffic was flowing again over a brand new structure with enhanced load capacity, seismic performance, and modern safety features. The I-95 bridge slide in Westport became a prime example of how advanced construction methods can be leveraged to perform full-scale bridge replacements in compressed timelines without sacrificing quality, safety, or functionality. Rising on the south shore of Lady Bird Lake, Waterline Tower is one of the most prominent high-rise construction projects associated with Austin's late 2020s development cycle, and in a 2026 context, it stands out as a project moving through the final stages required to convert a super tall structure into an occupied mixed-use building. The development combines residential, hotel, office, retail, and parking functions in a single vertical complex, making it more than a conventional apartment tower or office building. Its significance comes from both height and program density. It is designed to concentrate several major urban uses into one structure at a key downtown site, directly tied to the growth of Austin's skyline and central business district. The project's construction profile is defined by the demands of a very tall, reinforced concrete and steel high-rise built in a constrained urban environment. Earlier phases focus on excavation, foundation work, podium construction, vertical structural progression, floor plate formation, and the coordination of elevators, mechanical risers, and core systems. By the time a project like this enters the 2026 completion window, the central task is no longer simply adding height. The emphasis shifts to enclosure, systems activation, interior build-out, facade completion, and the commissioning work needed for each separate use within the tower. For a project approaching completion in 2026, the most important construction activities during that year would include finishing the curtain wall and exterior skin, completing waterproofing and roof assemblies, finalizing elevator installation and testing, and continuing the mechanical, electrical, plumbing, and fire life safety fit-out across the tower. Interior work becomes the dominant effort. Residential levels require unit completion, corridor finishes, life safety certification, and amenity installation. Hotel floors require guest room build-out, back-of-house systems, kitchens, service circulation, and hospitality-specific commissioning. Office components require lobby completion, vertical transportation readiness, tenant infrastructure, and the handover conditions needed for interior occupancy or later tenant improvements. Ground-level retail areas also move toward storefront completion, utility connection, and public access readiness. Another defining feature of a mixed-use tower like Waterline is that completion does not occur as one simple moment. Different parts of the building can move toward turnover on different sequences. Parking and base building systems may be ready before hotel interiors. Residential units can complete in batches. Retail shells may be delivered before tenant-specific fit-outs. Because of that, 2026 should be understood as the year of final construction execution and phased readiness rather than a single identical completion milestone for every component. In practice, this means the project's schedule is shaped by inspections, testing, punch list correction, systems balancing, facade closeout, and occupancy approvals as much as by visible structural work. On Miami's waterfront, the Fountain Bridge project is best understood in 2026 as a heavy civil job shaped by marine conditions, hurricane design loads, and the need to keep traffic moving while a new crossing is built. In the context of Miami area megaprojects under construction in 2026, this bridge work is defined less by what drivers will eventually see and more by what's happening in the water and below the roadway. The core construction activity in 2026 centers on foundations and marine works. Crews typically start by establishing work platforms, barges, and temporary trestles that allow drilling rigs and cranes to operate over the channel. Pile installation is the main schedule driver at this stage, with deep foundation piles drilled or driven into competent layers beneath soft marine sediments. Once piles are in, contractors build pile caps and pier tables, then begin erecting pier columns designed to resist vessel impact, storm surge forces, and long-term corrosion. Superstructure construction accelerates once piers are in place. In 2026, this commonly means setting precast concrete girders or assembling segmental box girder spans using cranes or a launching gantry. Each span is tied together with diaphragms, post-tensioning, and deck pours that create the final roadway surface. If the bridge includes a movable span or a special central opening for navigation, 2026 work also includes precision alignment of the mechanical bays, machinery rooms, and control systems that will govern openings, locking mechanisms, and safety interlocks. Approach roads and tie-ins are another active 2026 element. Miami bridge projects often require staged traffic shifts, so contractors build new approach embankments and walls first, then move traffic onto temporary alignments while the permanent connections are completed. Drainage and outfall systems are installed early because saltwater intrusion and intense rainfall events are constant design constraints. Electrical conduit banks, lighting foundations, and communications lines are also embedded during this phase to avoid later lane closures. Durability work is continuous in 2026. Concrete mixes, coatings, and reinforcing details are selected for a marine environment, and crews install corrosion protection measures like sealed joints, protective wraps, and high-performance barrier systems. Seawall interfaces, scour protection around piers, and shoreline stabilization are built in parallel, using rock armoring, geotextiles, and graded slopes to prevent undermining during storms. For timeline, bridge projects of this complexity are typically delivered in stages, with early milestones like first span set and deck continuity complete preceding final surfacing and commissioning. If the project is already in full construction by 2026, a common delivery pattern is substantial structural completion within roughly 18 to 36 months after major foundation work begins, followed by several months of testing, final paving, striping, and safety inspections before opening. The practical completion date depends on permitting, navigation windows, weather impacts, and supply chain timing for precast elements and mechanical components. At the intersection of logistics and land development on the south side of the Las Vegas Valley, the Sloan Arville Distribution Center is one of Nevada's active industrial megaprojects in 2026. It is being built as a high-throughput warehouse campus designed to support regional retail, e-commerce, and supplier distribution, with site planning optimized for constant truck circulation and fast inventory turns. In 2026, the project is in the heavy construction and fit-out window, where the building transitions from a shell into an operating facility. The main structure is typically delivered with tilt-up concrete walls and long-span steel framing, and this year's work includes completing roof decking, sealing the building envelope, and finishing the high-flatness concrete slab that's required for forklifts, automated equipment, and tall racking. As the slab cures, crews are cutting joints, applying surface hardeners where specified, and verifying tolerances that affect future automation performance. Dock infrastructure is a major 2026 focus. Contractors are installing dock doors, levelers, seals, and edge protection, while building out staging aprons and trailer parking areas. Yard paving and striping are progressing in phases, with heavy-duty asphalt sections placed first at the highest wheel load zones near dock approach lanes. Truck courts are being designed around turning radii for 53-foot trailers, so curb lines, bollards, and internal fencing are being set early to lock in circulation. Fire and life safety systems take center stage during this phase. In 2026, crews are installing ESFR, sprinkler piping, pump rooms, water storage where required, and the alarm and monitoring systems that tie the building into local response networks. Interior lighting, emergency egress routes, and exit signage are installed alongside these systems so the facility can move toward inspection and occupancy milestones. Electrical and data infrastructure is another defining scope item in 2026. Distribution centers rely on high-capacity service for conveyors, chargers, and IT, so switchgear, transformers, and panel boards are being installed, with conduit runs laid out to support flexible tenant layouts. If the facility includes automation, this is also the year when mezzanine platforms, conveyor supports, and equipment pads are built, followed by power drops and control wiring that connects scanners, sortation systems, and networked sensors. Office and employee support areas are typically built out in parallel. In 2026, that means framing and finishing for admin offices, break rooms, restrooms, and training rooms, along with HVAC zoning that separates conditioned office space from the large volume warehouse environment. Exterior work continues at the same time, including landscaping, stormwater basins, and perimeter security features such as controlled gates and camera-ready lighting poles. The San Joaquin Valley is one of the most active frontiers for large-scale renewable energy deployment in the United States. Central to this transformation is the Westlands Solar Park, a vast solar generation complex occupying former agricultural land in western Fresno and Kings counties. At full build-out, the project is planned to exceed 2,700 megawatts of solar photovoltaic generation capacity, with enough output to power over 1.2 million homes annually. Construction activity at Westlands is ongoing in multiple phases in 2026. Several hundred megawatts of new capacity are being installed this year alone, involving tracker-mounted solar panels, inverter stations, and substation upgrades across various parcels of the site. The terrain consists of retired farmland, much of it previously deemed unusable due to salt buildup and water supply restrictions. These parcels are being repurposed for renewable energy under a land use framework coordinated with the Westlands Water District and state energy planners. New transmission infrastructure is also under construction in 2026 to connect additional generating blocks to the California Independent System Operator grid. This includes expansion of the Gate substation and integration of newly completed collector substations. interconnection capacity is being increased to accommodate not only current solar projects, but also future energy storage systems that are now part of long-range build-out plans. In parallel with solar generation, battery energy storage is entering the construction pipeline. In 2026, multiple developers are installing utility-scale battery systems adjacent to solar arrays designed to store surplus daytime generation and discharge it during peak evening demand. These lithium-ion systems are being integrated directly with grid controls, supporting load balancing and reducing reliance on natural gas peaker plants. The development at Westlands is part of a larger regional shift. In 2026, the Western San Joaquin Valley hosts more than a dozen large renewable energy projects in various stages of permitting, construction, or operation. This includes both standalone solar fields and hybrid facilities with co-located batteries. Projects are distributed across counties, including Fresno, Kings, Kern, and Tulare, taking advantage of high solar irradiance, flat terrain, and proximity to major transmission corridors, such as Path 15 and the California-Oregon intertie. Permitting processes in 2026 have been streamlined under the state's renewable energy acceleration mandates, particularly those tied to SB 100 and the state's goal of reaching 100% zero-carbon electricity by 2045. Projects in Westlands benefit from environmental pre-clearance under the Renewable Energy Transmission Initiative, which has designated this area as a high-priority renewable energy zone. As a result, timelines from permitting to groundbreaking have shortened significantly in recent years. Employment across these projects in 2026 supports hundreds of construction jobs in electrical, civil, and mechanical trades. Labor agreements ensure prevailing wages and workforce training, while local agencies coordinate with developers on road improvements and service access. Equipment staging, panel deliveries, and interconnection work are active throughout the region, with multiple utility contractors working simultaneously across different sites. Few infrastructure projects in the northeastern United States have so comprehensively redefined regional mobility as the construction of the Governor Mario M. Cuomo Bridge. Spanning the Hudson River between Tarrytown and Nyack, this modern twin-span structure replaced the aging Tappan Zee Bridge, which had served for over 6 decades but was increasingly unable to meet the demands of 21st century traffic, safety, and structural performance requirements. The replacement effort was not only monumental in scale, but also served as a showcase of accelerated design build execution, seismic resilience, and long-span cable-stayed bridge engineering. Construction began with an extensive program of pile driving and cofferdam installation in the river's soft glacial sediments. More than 1,000 piles were driven to create the foundations for the main span towers and approach piers, with many of them extending over 200 feet below the river surface to reach competent strata. These piles were either steel pipe piles or concrete-filled steel cylinders driven using high-capacity hydraulic hammers aboard floating barges. Each pile had to be carefully aligned to meet strict tolerances, and dynamic load testing was performed regularly to verify bearing capacity. Central to the structure are the cable-stayed main spans, each carrying 4 lanes of traffic with additional space for emergency shoulders and a shared use path. The twin main span towers, constructed with reinforced concrete, rise from pile-supported cofferdams and were built incrementally using jump form systems. These towers house the anchorages for the stay cables, which are arranged in a semi-fan configuration and composed of galvanized steel strands enclosed in protective sheathing. Each cable was tensioned individually using strand jacks, and their load paths were continuously monitored throughout installation to maintain even deck camber and prevent distortion. The bridge's deck was constructed using precast concrete panels and structural steel girders. These panels were fabricated off-site and barged to the work zone, where they were lifted into place by gantry cranes and secured with high-strength post-tensioning systems. By utilizing modular construction, the project team reduced field labor intensity and maintained strict quality control over concrete finishes and rebar placement. Simultaneously, orthotropic deck sections were integrated into specific areas where weight savings were essential, particularly near the tower anchorages. Wind loads and thermal expansion across the bridge's more than 3-mile length were key design considerations. Expansion joints with built-in damping systems were installed at each abutment and tower transition. The bridge is also equipped with smart monitoring systems embedded within its structure, capable of measuring strain, tilt, temperature, and traffic load in real time. On the western span, a dedicated bicycle and pedestrian path was constructed, complete with belvederes for scenic viewing and interpretive signage. This element, though minor in structural weight, required careful coordination with the main deck construction to maintain alignment, loading distribution, and railing continuity. The lighting system was also integrated directly into the bridge structure, minimizing the need for maintenance access while providing full-spectrum LED visibility and programmable displays for special events. Linking hydropower from Canada directly into New York, the Champlain-Hudson Power Express is one of the most consequential transmission mega projects moving toward completion in the United States in 2026. The project is a long-distance, high-voltage direct current line designed to carry electricity from Quebec into New York City through a predominantly buried and underwater route. Its importance comes from both function and route strategy. Instead of relying mainly on new overhead corridors, the line is built largely beneath Lake Champlain, the Hudson River, and selected land segments, reducing surface disruption while creating a major new clean power connection into one of the country's largest electricity markets. The project consists of transmission cables, converter station infrastructure, landfall construction, buried terrestrial segments, underwater, installation works, interconnection facilities, and the control systems needed to operate an HVDC link across a long and technically varied corridor. Unlike a conventional generation project, this is an energy delivery mega project. Its value depends on whether the line can be physically installed, electrically integrated, and commissioned as a complete corridor. That makes the final construction period in 2026 especially important, because the system only becomes useful when the entire route and terminal equipment are ready together. The key construction work associated with 2026 completion is concentrated on the final cable installation segments, jointing and burial work, shoreline and transition point completion, and the finishing and energization of converter facilities. For a project using long submarine and underground cable runs, completion is not simply a matter of laying cable. Crews also have to complete trenching where required, backfill and protection measures, splice, vault work, cable testing, restoration of disturbed land segments, and the final interface between marine installed and land-based sections. Converter station work is equally critical, including installation of power electronics, transformers, cooling systems, protection equipment, control systems, and grid interconnection infrastructure. The schedule significance of 2026 is tied to the project's shift from corridor construction to electrical readiness. Earlier phases are dominated by permitting, manufacturing, route preparation, marine logistics, and initial installation campaigns. By the final approach to service, the project enters a more technical stage defined by testing and commissioning. High voltage direct current transmission requires extensive verification before operation. Insulation integrity, converter performance, communications, protection schemes, and system synchronization all have to be proven before the line can enter commercial service. That means the decisive work in 2026 includes not only physical construction, but also the final electrical and operational validation of the entire connection. By 2026, the Brightline Miami to Orlando corridor is less about building a brand new railway and more about expanding the capacity and reliability of an intercity system that now has to perform like daily infrastructure. In the Miami Megaproject context, the construction story in 2026 is a mix of corridor hardening, speed and schedule improvements, and station area build-outs that let the service handle higher ridership without degrading on-time performance. A major 2026 workstream is right-of-way and track capacity. Crews focus on additional double tracking in remaining single-track segments, plus new crossovers and turnouts that allow trains to pass and recover from delays. That work includes ballast and subgrade, improvements, replacement of rail fasteners and ties in high-wear zones, and drainage upgrades where South Florida rain events can saturate track beds and reduce stability. Bridge approaches and elevated sections receive structural inspections and targeted reinforcement so the line can maintain consistent speeds without imposing seasonal slow orders. Grade crossings remain a defining constraint for any Florida passenger line that runs at higher speeds. In 2026, construction activity typically concentrates on upgrading crossing surfaces, installing improved warning systems, and adding intrusion detection where feasible. Roadway tie-ins and traffic signal coordination near crossings are part of the same package, because the goal is not only safety, but fewer unplanned slowdowns caused by vehicle conflicts and queue spillback. Systems work expands in parallel. In 2026, signal and communications upgrades are key, including new equipment huts, fiber runs, and power conditioning systems that stabilize train control and dispatching. Where higher frequencies are planned, the corridor needs tighter block spacing and more resilient redundancy, so crews are installing and testing additional wayside hardware and networked monitoring equipment that feeds centralized operations. Stations and terminal interfaces also drive construction in 2026, especially around Miami Central and the Orlando Airport Terminal, where passenger volumes create pressure on circulation space. Work in this phase tends to include platform and canopy improvements, expanded vertical circulation, and upgraded passenger processing areas such as queuing, ticketing, and security adjacent zones. Back-of-house systems are upgraded too, including maintenance access, cleaning and servicing areas, and power distribution that supports more frequent departures. A less visible but critical 2026 construction program is resilience. Coastal South Florida infrastructure has to account for flooding, salt corrosion, and extreme heat. That pushes investment into corrosion protection, electrical room hardening, improved pumping, and drainage at low points, and redundant communications pathways so service can be restored quickly after severe weather. On the north end of the Las Vegas Strip corridor, the LVXP Resort and Arena concept represents a different kind of Nevada mega project in 2026. A hybrid development where a major entertainment venue is built as the anchor tenant, and the resort components are engineered around its event schedule, crowd flows, and broadcast demands. In 2026, when projects of this type are actively under construction, the work is less about decorative finishes and more about structural sequencing, utilities, and the back-of-house systems that allow an arena district to operate at high capacity. The arena drives the construction logic. In 2026, the critical path typically begins with deep foundations and substructure, because an arena requires long-span framing, heavy roof loads, and large, clear interior volumes. Crews focus on excavation, shoring, and concrete pours for lower bowls, service corridors, and loading docks. That below-grade work is paired with early construction of the event spine, meaning truck access, stage dock geometry, and the internal routes that move performers, broadcast gear, and concessions inventory without crossing public circulation. As the structure rises in 2026, steel erection becomes the visible milestone. Long-span trusses or space frame roof members are lifted in carefully planned picks because the roof supports lighting grids, rigging points, catwalks, and the mechanical systems that keep the building comfortable during peak occupancy. Bowl construction advances simultaneously with stepped seating rakers, concourse slabs, and vertical cores for elevators and stairs, progressing on a repetitive schedule that allows multiple trades to work in parallel. Mechanical and electrical work accelerates early for an arena. In 2026, contractors install large air handling units, smoke control systems, and zoned ventilation designed for quick turnover between events. Electrical crews build redundant power distribution for show lighting, scoreboard systems, production booths, kitchens, and security. Low voltage systems are not an afterthought. They are part of the build, with fiber backbones, camera infrastructure, access control, and networked life safety systems being roughed in as soon as areas are enclosed. Resort construction, when paired with an arena, tends to be sequenced to keep the public-facing pieces aligned with venue readiness. In 2026, that typically means podium-level work first. Retail shells, food and beverage back of house, shared loading, and pedestrian circulation. If the project includes hotel towers, their cores and floor plates follow a steady concrete cycle, while facade installation begins on lower floors to create weather-tight zones for interior fit-out. Site work is a major part of 2026 activity. Roadway tie-ins, rideshare staging, parking access, and pedestrian safety features are built early because arena peaks are short, intense surges. Utility upgrades are also continuous in this phase, including new water and sewer capacity, stormwater systems sized for large paved areas, and electrical service improvements to handle high event loads. One of the most complex airport infrastructure undertakings in the United States is nearing critical completion at Los Angeles International Airport in 2026. The Landside Access Modernization Program, or LAMP, is a $5.5 billion capital investment project reshaping ground transportation access to LAX. Its core components are designed to eliminate decades of congestion by reconfiguring how passengers arrive at and depart from one of the busiest airports in the world. At the center of the program is the 2.25-mile automated people mover, an elevated train system that will connect terminals to new off-site facilities. By 2026, all 6 stations of the APM are in advanced phases of construction. Guideway installation is complete, and systems integration is actively underway. This includes communications, train control, traction power, and platform screen doors. Testing of the first train sets began in 2024, and full pre-revenue operations are scheduled for mid-2026, with the line expected to open to the public later in the year. The APM will operate 24 hours a day, with peak headways of under 3 minutes, linking the central terminal area with 3 major intermodal access points: the Consolidated Rent-A-Car Facility, the Intermodal Transportation Facility, West, and the future Airport Metro Connector Station at 96th Street. These access points are critical to shifting passenger movement away from curbside traffic. Construction of the Conrack facility is substantially complete in 2026. Located east of the 405 freeway, this 5.3 million square foot structure consolidates over 20 rental car operations into a single vertical facility, reducing shuttle trips by over 3,000 daily. The facility includes ready return areas, maintenance bays, fueling stations, and direct access to the APM. Operational turnover to rental car companies began in late 2025, with phased occupancy continuing through 2026. The ITF West, a major drop-off and pickup location with public parking, opened in 2021, but continues to evolve in 2026 with integration of pedestrian pathways, wayfinding systems, and last-mile transit connections. The facility includes nearly 4,300 parking spaces and serves as the western terminus of the APM. It also supports the broader mobility plan by acting as a ground transportation hub with connections to shuttles, rideshare services, and regional buses. On the eastern side of the system, construction of the Airport Metro Connector Station, led by LA Metro, is active in 2026. This facility will link the APM to the regional rail network via the Metro K line and future expansions. Platform structure, track installation, and system integration are progressing, with projected completion targeted for 2027. When operational, it will allow passengers to reach LAX from the metro system without the need for a vehicle. Additional work in 2026 includes extensive roadway realignment within the central terminal area. This involves upgrading access roads, curbs, and signage to match the new passenger circulation model, including drop-off lanes designed for rapid movement to the APM platforms. Pedestrian bridges linking terminals to the APM stations are in final construction stages, involving glass installation, elevator commissioning, and ADA compliance checks. The LAMP project also integrates sustainability features. Solar panels, electric, vehicle infrastructure, and stormwater capture systems are being commissioned across multiple facilities. The APM itself is all electric, designed to reduce greenhouse gas emissions by over 30,000 metric tons annually once fully operational. As the rising arc of twin basket handle arch bridges took shape over the Mississippi River, the transformation of the I-74 corridor between Bettendorf, Iowa, and Moline, Illinois, entered one of its most critical and technically ambitious phases. The construction of the new I-74 Mississippi River Bridge was not merely a replacement of aging infrastructure, it was a complete reimagining of regional connectivity, driven by modern standards for traffic volume, safety, and structural resilience. The original bridge system, composed of two separate spans constructed decades apart, had long been overcapacity and structurally obsolete, necessitating a solution that would carry 4 lanes of traffic in each direction, with substantial shoulders and multimodal accommodations. Foundation work for the main river crossing demanded meticulous geotechnical investigations due to the presence of complex riverbed conditions. Deep caissons and drilled shafts were deployed to reach competent rock, with many of the drilled shafts extending over 100 feet into the bedrock below the Mississippi's muddy floor. This phase involved the use of massive steel casing, oscillators, and reverse circulation drilling techniques to ensure shaft integrity in an environment challenged by underwater currents and variable sediment layers. Cofferdams were constructed to create dry working conditions for pier construction, each one engineered to resist the high hydrostatic pressures of the river during seasonal flooding. The signature basket handle arch design was selected for both aesthetic and structural performance. These arches rise more than 100 feet above the deck and were fabricated in large segments off-site, then transported by barge to the erection location. The erection sequence was tightly choreographed. Arch ribs were lifted and pinned using floating cranes during periods of calm river flow, with crews performing high elevation bolting and welding operations within tight tolerances. Each arch rib section was temporarily braced and connected via knuckle joints and box diaphragms until the entire arch structure was self-supporting. The steel itself was weathering grade, chosen to reduce long-term maintenance needs and withstand the extreme freeze-thaw cycles common to the upper Midwest. Suspended below each arch is a post-tensioned concrete deck carried by steel hangers arrayed in a vertical configuration. The bridge deck was cast in place, using a traveling formwork system that advanced span by span. Epoxy-coated rebar, high-performance concrete mixers, and continuous monitoring of curing conditions ensured long-term durability. Expansion joints were minimized through the use of integral abutments and deck continuity, reducing maintenance complexity. Parallel to the main river spans, approach structures on either side required extensive reconstruction and realignment of existing highway infrastructure. Mechanically stabilized earth walls and drilled shaft-supported piers form the backbone of the approaches. The coordination of traffic staging during construction was a major challenge, as portions of the existing bridge needed to remain in service throughout the process. Temporary crossovers, stage demolitions, and nighttime steel girder installations were part of a detailed traffic management strategy. Set within Exposition Park in Los Angeles, the Lucas Museum of Narrative Art is one of the most distinctive cultural construction projects advancing toward completion in the United States in 2026. The project is designed as a major museum dedicated to narrative art in multiple forms, including illustration, painting, photography, comics, cinema-related material, and digital media, with a building program that also includes galleries, theaters, educational space, archives, public landscape, and visitor facilities. Its significance in the 2026 construction cycle comes from the fact that it is not a standard institutional building. It combines complex architecture, specialized museum systems, and extensive site integration in one of Los Angeles' most important civic districts. The structure itself is central to the project's identity. Unlike a conventional rectangular museum, the building is defined by a sculptural form with a continuous exterior envelope and a highly controlled interior environment. That architectural approach creates additional complexity in both construction and completion. The work is not limited to erecting floor plates and closing a facade. It requires precise coordination between structural systems, exterior cladding, waterproofing, environmental controls, and the interior gallery conditions needed for long-term preservation of artworks and archival materials. By the time the project reaches its 2026 completion phase, the most important work is concentrated on final enclosure, systems commissioning, interior fit-out, and landscape integration. Exterior construction in that period includes completion of the outer skin, sealing of the building envelope, roof finishing, drainage resolution, and the final detailing, required to protect the structure and create stable internal environmental performance. Inside the museum, the key construction activities include gallery finishing, installation of climate control systems, lighting systems, fire protection, security infrastructure, vertical transportation, theater and presentation spaces, back-of-house support areas, and the specialized mechanical and electrical systems required for museum operations. A museum of this type also depends on exact environmental calibration before it can function. Completion is not achieved when the building is visually finished. The project has to move through balancing and testing of temperature and humidity controls, life safety certification, access control integration, audio-visual commissioning, and the preparation of collection handling spaces. Exhibition areas require carefully controlled lighting and air management. Storage and archive areas need stricter performance standards than many ordinary public buildings. That makes the final year of construction particularly technical because the project is transitioning from architectural completion into operational readiness. Away from the spotlight of game day, UNLV's football infrastructure work in Nevada in 2026 is centered on the facilities that determine week-to-week performance. Practice fields, player development spaces, and the technical backbone that supports modern college athletics. The stadium itself is only one piece of the system, and the 2026 construction focus is on improving the places where training, rehab, scouting, and operations happen every day. In 2026, a major share of the work is typically concentrated on the field environment. That means rebuilding practice surfaces with updated turf systems or improved natural grass profiles, adding better sub-drainage, and upgrading irrigation controls to handle extreme heat and water efficiency requirements. Field lighting upgrades are part of this package, with higher output LED arrays and improved aiming to support night training while reducing spill and energy use. Where fields are being regraded, crews also rebuild perimeter curbs, safety runoff zones, and fencing designed for controlled access and equipment movement. Inside the football operations and performance spaces, 2026 construction is about capacity and workflow. Strength and conditioning areas are expanded with higher floor load design for heavy equipment, improved ventilation for high occupancy training periods, and acoustical treatment to reduce echo in large rooms. Athletic training and sports medicine build-outs add dedicated hydrotherapy, physical therapy bays, and recovery zones, all requiring specialized plumbing, floor waterproofing, and electrical distribution for medical equipment. Player spaces are another focus in 2026, especially locker room and meeting room modernization. Renovations typically include larger locker footprints, improved showers and laundry routing, and better circulation so the building handles peak team movement before and after practices. Team meeting rooms and position rooms are upgraded with integrated AV, coach-to-player video systems, and data connectivity that supports film review and analytics. That drives a major 2026 scope item that doesn't read as dramatic on camera, but matters in construction. Structured cabling, server closets, Wi-Fi densification, and power conditioning for always-on broadcast and video gear. Stadium-adjacent upgrades in 2026 often involve operational efficiency and athlete logistics rather than visible architecture. This includes improved equipment storage, loading access for trucks and carts, secure entry points, and revised pedestrian paths that separate athlete movement from public circulation. If premium or fan-facing areas are part of the scope, 2026 work may also include targeted concourse improvements, upgraded concessions, back-of-house systems, and point-of-sale network expansion, all tied to electrical and data upgrades. The Pacheco Pass segment falls within the broader Merced to San Jose section, which is in the advanced pre-construction phase. Full-scale construction is expected to begin in late 2026 or early 2027, following the completion of design, environmental permitting, and contractor procurement. In 2026, geotechnical investigations are being conducted at multiple points across the alignment, including test drilling to analyze subsurface conditions, fault mapping near the Calaveras and San Andreas fault zones, and seismic risk assessments required for final tunnel engineering. The tunnel alignment will require 2 main bores with an internal diameter of approximately 40 feet each, separated by cross passages every 1,000 to 1,500 feet to allow emergency access and pressure equalization. An intermediate access shaft is also planned in the vicinity of Casa de Fruta to provide tunnel boring machine launch capability and logistical support during construction. The geology of the Diablo Range presents significant challenges with faulted rock zones, variable water inflows, and compressible soils in valley transitions. Tunneling will be conducted using pressurized tunnel boring machines capable of navigating mixed face and high pressure conditions. The Pacheco Pass tunnels will pass under critical infrastructure, protected habitat areas, and seismic fault lines, requiring advanced lining systems and continuous monitoring. Designs include seismic isolation joints and drainage galleries to mitigate fault displacement risk and groundwater intrusion. Tunnel depth will range from 100 to over 1,000 feet below surface, depending on terrain. Ventilation and safety systems, including emergency egress, fire protection, and pressurization controls, are part of the ongoing systems design effort in 2026. Upon completion, the tunnels will enable a seamless high-speed rail corridor from Merced to Gilroy, reducing rail travel time across the pass from over an hour to just under 15 minutes. Combined with viaducts, embankments, and cut and fill, sections across the San Joaquin Valley and into the Santa Clara Valley, the Pacheco Pass alignment represents one of the most capital-intensive and engineering-heavy components of the entire HSR system. The full Merced to San Jose segment is targeted for phased operational readiness beginning in the early 2030s, contingent on funding and right-of-way clearance. In 2026, contract packaging and procurement strategy are being finalized. The tunnel construction will likely be delivered as part of a design-build package, integrating civil structures, systems, and tunnel fit-out under a single delivery framework. Coordination with Caltrain and Union Pacific Railroad in the Gilroy area is also active in 2026, where blended operations with existing rail infrastructure are being planned. At full build-out, the Pacheco Pass tunnels will serve as the gateway between the Central Valley's agricultural and inland urban centers and the tech-driven economy of Northern California. The tunnels are expected to handle multiple high-speed rail trains per hour in each direction, forming a high-capacity backbone for statewide intercity travel. Their construction, once launched, will take an estimated 6 to 7 years, involving around-the-clock excavation and a continuous logistics chain to manage spoil removal, liner segment installation, and tunnel utility integration. Off the coast of Virginia, the Coastal Virginia Offshore Wind Project is scheduled to reach its defining construction phase in 2026, when the offshore installation campaign and grid connection work are expected to push the development from a marine works program into an operating energy asset. This is one of the largest energy megaprojects advancing toward completion in the United States, built to establish a commercial-scale offshore wind facility in federal waters east of Virginia Beach and to deliver a major new source of electricity into the regional grid. The project consists of a large field of offshore wind turbines, subsea cable systems, offshore substations, onshore transmission connections, and the related port and logistics infrastructure needed to assemble, transport, and install heavy components at sea. Its scale makes it different from earlier US offshore wind efforts. This is not a pilot installation or a small demonstration array. It is a utility-scale generation project intended to add substantial capacity through a coordinated marine construction effort involving specialized vessels, fabrication supply chains, and grid integration works on land. The most important construction activity associated with completion in 2026 is the offshore erection sequence. By that stage, work is focused on installing turbine foundations, transition pieces, towers, nacelles, and blades, along with completing offshore substations and laying or finishing inter-array and export cables. Each of these activities depends on weather windows, vessel availability, marine coordination, and strict sequencing. Foundation and cable work must be sufficiently advanced before final turbine installation can move efficiently, and energization cannot occur until both offshore and onshore systems are ready for integrated testing. Onshore construction in 2026 is also essential to completion. That includes cable landfall works, underground or corridor-based transmission connections, substation completion, electrical equipment installation, control systems integration, and final commissioning preparations. For a project of this kind, completion is not defined only by the last turbine standing offshore. It depends on the point when generation equipment, transmission, infrastructure, protection systems, and grid connection assets are all tested together and accepted for service.